Hello and welcome to Sleepy Science. What if matter is not solid, stable, or simple at all, but a hidden machine waiting for the right condition to reveal its stranger face? In this journey, we'll explore materials that bend waves the wrong way, metals that remember their shape, liquids that climb walls, light that slows almost like it's moving through honey, crystals that respond to light, glass that changes transparency, and matter so dense or delicate it seems to break everything school taught us about reality. These are not myths, magic tricks, or exaggerated science headlines. They are real discoveries from physics, chemistry, and materials science, showing that the world around you is not made of ordinary stuff, but of matter with secret behaviors, hidden phases, and impossible-looking rules. So tap like, hit subscribe, and step into the strange science of materials that make reality feel far less solid than it seems. Matter that behaves like it has negative mass. Imagine pushing something gently forward, and instead of moving away from your hand, it seems to accelerate back toward the push, as if matter itself has misunderstood the simplest rule you were ever taught. That is the strange doorway opened by matter that behaves like it has negative mass. Not in the exaggerated sense of a magical object floating against gravity or a science fiction engine breaking the universe, but in a real and carefully controlled physical sense where a material system responds to force in a way that feels almost backwards. In ordinary life, mass feels like resistance. You push a chair and it moves in the direction you push. You kick a ball and it flies away from your foot. Even if the object is heavy, slow, slippery, or stubborn, the basic rule remains familiar. Force points one way, motion answers in the same general direction. But deep inside certain quantum systems, especially under extreme laboratory conditions, that rule can be bent. Scientists have created situations where particles do not have negative mass in the simple everyday meaning, but negative effective mass, which means the particles behave as if their resistance to motion has flipped sign. The key word is effective. It does not mean someone has bottled anti-gravity or made a stone that naturally falls upward. It means the environment around the particles has been engineered so precisely that their motion through that environment follows rules no ordinary object would follow in open space. To understand this gently, think of a person walking on a moving walkway at an airport. Their own body has not changed, but the surface beneath them changes how their motion appears. Or imagine rolling a ball across a strange landscape of hills and valleys, so carefully shaped that the ball's response no longer matches your simple expectation. In quantum materials, the landscape is not made of visible hills, but of energy, momentum, lasers, magnetic-like interactions, and the shared behavior of many atoms acting together. One of the most famous demonstrations used atoms of rubidium cooled to temperatures so close to absolute zero that the atoms stopped behaving like separate tiny particles and began acting more like one collective quantum wave, a state called a Bose-Einstein condensate. At that point, the atoms are not hot, chaotic, and independent the way gas molecules are in the air around you. They become unusually orderly, almost like a quiet crowd breathing in the same rhythm. Then, researchers used lasers to change the way these atoms moved, linking their internal spin-like properties with their motion. Under these conditions, part of the condensate entered a region where its effective mass became negative. When the system was pushed or allowed to expand, it did not simply spread like a normal cloud. It could slow, form ripples, become unstable, or show self-trapping behavior, as if the quantum fluid were resisting motion in the wrong direction. This is what makes the phenomenon so fascinating. The atoms themselves were not transformed into impossible matter, but the rules governing their collective motion were rewritten. And that teaches you something deeper than the headline. Matter is not only what it is made of. Matter is also how it is arranged, how it is constrained, and what kind of invisible rules shape its movement. A block of metal, a cloud of ultra-cold atoms, a crystal, and a living cell may all be made from familiar particles. Yet their behaviors can differ so wildly that they feel like different languages spoken by the same alphabet. Negative effective mass is one of those moments when nature reminds you that mass is not always just a simple amount of stuff. In everyday life, mass tells you how strongly something resists acceleration. But inside materials, especially quantum materials, particles often behave like travelers, moving through a crowded city rather than empty space. Their motion depends on the streets, the traffic rules, the slopes, the signals, and the hidden architecture around them. In solids, scientists often speak of electrons as if they have an effective mass because the crystal around them changes how they move. Sometimes electrons can even leave behind empty spaces called holes, and those holes can behave like particles with their own strange properties. So the idea that matter can behave as if its mass has changed is not just a trick. It is one of the ways modern physics understands materials. Negative effective mass is the extreme, unsettling version of that idea. It shows that when you control a system carefully enough, you can make motion answer force in a way that seems to contradict common sense without actually breaking physical law. That distinction matters. If someone says negative mass has been created and then claims it proves warp drives, floating cities, or impossible energy machines are now real, they are stretching the truth far beyond the science. The real discovery is quieter, but in many ways more beautiful. It shows that the universe has layers of behavior hidden beneath the surface of ordinary experience. It shows that the same matter you think you understand can become strange when cooled, organized, and guided into rare states. It shows that physics is not just a list of fixed rules, but a set of relationships between objects and the conditions around them. You do not need to lie about it to feel wonder. The truth is already strange enough. A gas cooled almost to stillness can become a single quantum fluid. Lasers can reshape the rules of its motion. A push can produce a response that feels reversed. A cloud of atoms can behave less like dust in the air and more like a thought moving through an invisible maze. And when you sit with that, the lesson becomes larger than the laboratory. You begin to realize that many things in nature are not defined only by their ingredients, but by their context. Carbon can be soft graphite or diamond. Water can be liquid, ice, vapor, or something stranger under pressure. Electrons can flow with resistance in one material and almost without resistance in another. And atoms that seem ordinary alone can become extraordinary together. Negative effective mass belongs to this family of hidden possibilities. It asks you to stop seeing matter as dead, simple, and already understood. It asks you to imagine reality not as a pile of objects, but as a field of behaviors waiting for the right conditions to reveal themselves. And maybe that is the quiet, emotional pull of this science. It reminds you that what something becomes depends not only on what it is, but on the world it is placed inside. Under ordinary conditions, matter follows ordinary rules. But change the temperature, change the structure, change the invisible landscape around it, and matter begins to show another face. A face that does not shout, does not pretend, does not need fantasy to be powerful. It simply waits at the edge of what you thought was obvious. And when you finally reach it, it turns the simplest gesture in physics, a push, into a question. What else in the world only seems normal because you have never seen the conditions that would make it become strange? Materials that hide objects from certain waves. A wall does not have to vanish to become hidden. Sometimes it only has to persuade the wave looking for it to walk around and continue as if nothing was ever there. This is the real science behind materials that hide objects from certain waves. And the first thing to understand is that this is not the fantasy version of invisibility, where a person throws on a cloak and disappears from every eye, every camera, every direction, and every color of light. The truth is narrower, but much more interesting. Some specially engineered materials can guide particular waves, such as microwaves, sound waves, heat flow, or even certain vibrations, so that those waves bend around an object instead of scattering from it in the usual way. In 2006, researchers at Duke University demonstrated one of the first working electromagnetic cloaks, not for visible light but for microwaves. Using a carefully structured metamaterial, that guided microwave beams around a hidden region with less disturbance than an ordinary object would create. That word, metamaterial, is important because the magic is not in a strange new element pulled from another planet, but in structure. These materials are designed with patterns smaller than the waves they are meant to control, like tiny artificial architecture built into the material itself. A normal material responds to waves because of what its atoms naturally do. A metamaterial responds because humans have arranged its inner geometry so precisely that the wave experiences it as something nature rarely provides on its own. It is a little like building a city where every street, tunnel, corner, and bridge is designed to redirect traffic without the drivers noticing the obstacle in the center. The wave comes in, meets the material, and instead of bouncing back, revealing the object or leaving a shadow, it is encouraged to curve around the hidden space and rejoin on the other side. To the wave, the object becomes quieter, less present, almost erased, but only almost, and only under the right conditions. That is where the real lesson begins. Cloaking is not the same thing as making something universally invisible. A cloak that works for microwaves may do nothing for visible light because visible light has much shorter wavelengths and requires much finer structures. A design that hides something from one direction may fail from another. A cloak that works at one frequency may reveal the object at a different frequency. Even researchers who study these ideas openly emphasize that practical cloaking is limited by bandwidth, size, direction, loss, and imperfections in the material. So the honest version is not, we have Harry Potter's cloak. The honest version is more subtle. We have learned that visibility is not simply about whether an object exists, but about how waves interact with it. You see things because light scatters from them into your eyes. Radar detects aircraft because radio waves bounce back. Sonar detects underwater objects because sound waves reflect. Even heat and vibration can reveal hidden structures by the way they flow, bend, scatter, or slow down. If you can reduce that disturbance, you reduce the object's signature. You do not delete the object from reality. You make it harder for a specific kind of wave to notice it. And that idea opens a strange window into what being visible really means. Something can be visible to your eyes but hidden from radar. Something can be obvious to sound but quiet to heat. Something can be physically present yet nearly absent to the measuring system trying to detect it. In acoustic cloaking, for example, scientists study structures that guide sound around obstacles, so the sound field behind them is less disturbed, a concept connected to transformation acoustics and engineered material properties. Similar thinking has been explored for other waves too, including water waves, elastic waves, and seismic vibrations. Though real-world control of large, messy waves is extremely difficult and far from a simple shield around buildings. This is why the subject is so powerful for the imagination without needing to become dishonest. It teaches that reality is partly a conversation between an object and the waves that reveal it. A stone in total darkness has not disappeared, but without light reaching your eyes, it has left your visual world. A silent submarine is still there, but if it scatters less sound back to sonar, it becomes less present to that system. A microscopic object may be impossible to see with certain wavelengths because the waves are too large to resolve it clearly. Every act of detection has limits. Every sensor asks reality a particular kind of question. And metamaterials are a way of shaping the answer. In a deeper sense, these materials do not just hide objects. They expose how detection works. They remind you that what you call appearance is really evidence. A wave touches something, changes direction, returns altered, and your instrument turns that alteration into knowledge. Remove the disturbance and knowledge begins to fade. That should make you pause, because it means the visible world is not simply the world itself. It is the world after waves have negotiated with matter and returned with a report. Metamaterial cloaking edits that report. It does not destroy the truth, but it changes how loudly the truth announces itself. And perhaps that is the quiet wonder here. The universe is full of things that are known only because they interrupt something else. A planet interrupts starlight. A tumor interrupts an X-ray image. A submarine interrupts sound. A hand interrupts light and casts a shadow. To hide something from a wave is to smooth over the interruption, to make space behave as if the object were less sharply there. Not gone, not impossible, just less detectable in one chosen language of nature. And when you understand that, the idea of invisibility becomes both less magical and more profound. It is not about escaping existence. It is about controlling interaction. It is about learning that matter does not reveal itself equally to every observer, every instrument, or every wave. The object may remain solid, heavy, and real, but to the right wave, under the right conditions, it can become a kind of silence. And maybe that is what makes these materials so haunting. They show that hiding is not always darkness, deception, or emptiness. Sometimes hiding is geometry. Sometimes it is structure. Sometimes it is a wave being guided so carefully around a secret that it never knows a secret was there at all. Liquids that climb walls and defy friction. There is a liquid so cold that it stops behaving like something poured and starts behaving like a secret, trying to escape its own container. You can place it in a cup, watch it settle, and still it may creep upward in a thin, invisible film, slide over the rim, and gather outside as droplets, almost as if gravity has become a suggestion rather than a command. This is not a myth, and it is not ordinary water performing a trick. It is superfluid helium, one of the strangest real states of matter ever observed. And it appears when helium-4 is cooled below about 2.17 Kelvin, a temperature so close to absolute zero that the noisy motion of atoms becomes quiet enough for quantum behavior to rise into the visible world. At that point, the helium enters a state often called helium-2, where part of the liquid can flow with no ordinary viscosity, meaning it has no internal thickness or stickiness resisting its motion in the familiar way. That does not mean it can do anything, and it does not mean friction has disappeared from the universe. It means that under these very specific conditions, the superfluid part of helium can move through tiny openings and along surfaces with an ease that feels impossible when compared with everyday liquids. Honey drags, oil slips slowly, water splashes and settles. But superfluid helium seems to search for paths too small, too thin, too hidden for normal fluids, forming what is known as a rollin film that can coat the inside of a container, crawl up the walls, and continue down the outside if the container is open. This strange climbing happens because helium atoms are attracted to the surface enough to wet it, and once the thin film exists, the superfluid component can flow through it with almost no ordinary resistance holding it back. The result looks like a liquid disobeying gravity, but the more honest explanation is even more beautiful. Gravity is still there, yet surface forces, quantum flow, and the absence of viscosity in the superfluid component allow the liquid to move in ways your everyday intuition was never built to expect. Researchers and educators often describe this creeping film as one of the dramatic signs of superfluidity, alongside the fountain effect, where superfluid helium can move through a tiny porous plug and rise in a jet when heated slightly. Think about what this means. A normal liquid is a crowd of atoms bumping, jostling, and losing energy as they move past one another. That internal rubbing is what makes motion fade. Stir a cup of coffee and the swirl dies. Spin water in a bowl and eventually it slows. But a superfluid is different because the atoms enter a shared quantum condition, not as separate little marbles rolling independently, but as a collective state with a kind of deep coordination. The liquid does not become alive, but it does become unified in a way that ordinary experience almost never shows you. This is why superfluid helium can flow through extremely narrow channels that would stop normal liquids, and why a current in a superfluid can persist for a very long time when conditions are right. But there are limits, and those limits matter. If the flow becomes too fast, or the container is rough, or heat enters the system, tiny disturbances and vortices can appear, and the perfect smoothness begins to break. So the real story is not a liquid with no rules. The real story is a liquid that reveals a deeper set of rules, rules that only appear when matter is cooled so far that the ordinary chaos of heat no longer hides them. It teaches you that friction, something you feel every day in your shoes, your hands, your machines, your breath moving through air, is not a permanent feature of all motion. It is a behavior that depends on the state of matter, the temperature, the surface, the scale, and the hidden order inside the system. Superfluid helium is powerful because it takes something familiar, liquid, and removes one of the qualities you thought every liquid had. It still has weight. It still occupies space. It still must obey energy and conservation laws. Yet it moves with a quiet strangeness that makes the ordinary world feel suddenly incomplete. And perhaps that is the deeper lesson hiding in the cold. Matter is not finished being understood just because it looks simple at room temperature. A cup of liquid can become a quantum object. A surface can become a path. A container can fail, not because it breaks, but because the liquid inside has found a film-thin way to leave. When you imagine superfluid helium climbing a wall, do not picture magic. Picture nature under extreme calm, stripped of its thermal noise, revealing a behavior that was always allowed but almost never seen. And maybe that is why this phenomenon stays with you. It shows that resistance, even in physics, is not always fundamental. Sometimes resistance is only what appears when the world is warm, noisy, and ordinary. Cool matter close enough to stillness, and it begins to whisper a different truth. That movement can become almost effortless, that surfaces can become rivers, and that even a liquid can seem to dream of escape. Light that slows down like it's moving through honey. Light is supposed to be the fastest thing you can imagine. So the moment you hear that scientists have slowed it down to the speed of a bicycle, your mind almost refuses to accept the sentence. In empty space, light moves at the cosmic speed limit, racing so fast that a beam could circle Earth several times in a single second, and nothing with information can outrun it. But light does not always travel through emptiness. It passes through glass, water, air, crystals, gases, and strange laboratory-made environments. And inside those materials, something subtle happens. The light is not simply a tiny bullet flying through a tunnel. It is an electromagnetic wave interacting with the charged particles inside matter, disturbing them, being delayed by them, and then continuing forward as a combined motion of light and material response. That is why light moves more slowly in glass than in vacuum, and why a straw looks bent in a cup of water. But the truly astonishing story begins when scientists learned how to slow not just a little, but enormously. In 1999, Lena Howe and her team used an ultra-cold cloud of sodium atoms to slow a pulse of light to around 17 meters per second. A speed you could imagine someone running beside. This did not mean the universe's speed limit was broken, and it did not mean individual light particles forgot how fast light is supposed to be in empty space. What slowed was the pulse, the packet of light carrying shape and information, as it moved through a specially prepared medium. The method used a phenomenon called electromagnetically induced transparency. But you do not need heavy mathematics to feel what that means. Normally, a cloud of atoms might absorb certain light, blocking it like fog swallowing a flashlight beam. But when another carefully tuned laser is applied, the atoms can be placed into a delicate condition where they stop absorbing the light and instead let it pass through, while also delaying it dramatically. It is as if the material opens a narrow, quiet doorway for the light, but that doorway is filled with invisible hands that gently hold the pulse back. The light becomes partly light and partly a pattern written into the atoms, a shared state where the pulse drags its own shadow through matter. This is why the phrase "moving through honey" feels emotionally right, even if the science is not about stickiness. Honey slows a spoon through thickness. Cold atoms slow a light pulse through interaction. One is ordinary friction. The other is a carefully arranged conversation between radiation and matter. And that difference matters, because the real wonder here is not that light becomes tired or heavy, but that its motion can be shaped by the inner structure of the material it crosses. Later experiments went even further. and showed that under the right conditions, a light pulse could be effectively stopped, stored as an atomic pattern, and then released again as light. This sounds almost impossible until you understand that the light was not frozen like an object in ice. Its information was transferred into the atoms, held briefly as a kind of material memory, then converted back into a moving pulse. Imagine whispering into a room and having the air itself remember the exact shape of your whisper, waiting in silence until someone tells it to speak again. That is not magic. It is one of the most delicate forms of control modern physics has achieved, and it teaches something profound about light itself. We often think of light as pure speed, pure escape, pure motion, but inside matter, light can become patient. It can be delayed, reshaped, stored, and released. It can carry information not only across space, but into the hidden states of atoms. This is why slow light matters beyond the wonder of the number. It points toward technologies involving optical communication, quantum information, precision sensing, and ways of controlling signals without instantly turning everything into electronics. In ordinary computers and networks, information is constantly being converted, delayed, amplified, and routed. Light is excellent for carrying information quickly, but speed alone is not enough. Sometimes you need control, timing, memory, and synchronization. Slow light gives researchers a way to ask whether light can be guided with the delicacy of a musical note rather than the bluntness of a thrown stone. Still, the truth must stay clear. You cannot pour slow light into a jar. You cannot watch a beam crawl across your bedroom wall. These effects require carefully prepared materials, precise lasers, and conditions that often exist only in advanced laboratories. The slowed pulse is not a glowing marble moving slowly enough for your eyes to follow. It is a change in how the pulse travels through a medium. But even with those limits, the idea remains breathtaking, because it reveals how different nature becomes when you stop treating familiar things as simple. Light is not only brightness. Matter is not only substance. When the two meet under the right conditions, speed becomes adjustable, emptiness becomes memory, and a beam that normally races beyond imagination can be made to linger. Perhaps that is why slow light feels so haunting. It takes the symbol of urgency itself and teaches it to pause. It shows you that even the fastest thing in your world can be delayed by the right environment. Not broken, not defeated, just invited into a deeper relationship with matter. And maybe that is the quiet question this science leaves behind. If light, the great messenger of the universe, can be slowed, held, and released by atoms arranged with enough care, how many other things that seem unstoppable are only waiting for the right conditions to reveal a slower, stranger truth? The strange matter inside neutron stars. A neutron star is what happens when a dead giant star squeezes matter so violently that atoms lose the empty spaces that once made them feel ordinary. In the life you know, matter has room inside it. Electrons move around atomic nuclei. Objects seem solid because forces hold them apart, not because every part of them is packed full. But inside a neutron star, after a massive star collapses in a supernova, that familiar architecture is crushed almost beyond recognition. The remnant can hold more mass than the sun inside a sphere roughly the size of a city, creating one of the densest stable forms of matter known in the universe. NASA describes a neutron star as the imploded core left behind by a supernova, with an outer crust and an extremely dense interior, where the normal separation between particles has been forced into a new state. The outermost layer may begin with something almost understandable, a rigid crust made of nuclei and electrons, under gravity so intense that a mountain there could be microscopic and still hold enormous energy. But as you go deeper, the pressure rises until electrons and protons are pushed together, creating more and more neutrons, and the matter stops resembling anything you could place on a table. Near the bottom of the crust, scientists expect bizarre nuclear shapes, sometimes called nuclear pasta, not because it is soft or edible, but because competing forces can arrange nuclear matter into long rods, flat sheets, tubes, and tangled structures that resemble spaghetti or lasagna. in name only. This is not a joke added for attention. It is a serious idea in nuclear astrophysics, and studies suggest these pasta-like layers may be incredibly stiff because of their density and shape. Beneath that crust, the real mystery begins. The core is likely dominated by neutrons packed so tightly that the behavior of matter depends on nuclear physics we cannot fully reproduce on Earth. We can smash particles together for tiny moments in laboratories, and we can measure atomic nuclei, but we cannot hold a piece of neutron star core in a container. So scientists study these stars from far away, using X-rays, pulsar timing, gravitational waves from neutron star mergers, and careful models of how dense matter should behave. The question they are trying to answer is simple to say, and extremely difficult to solve. When matter is compressed beyond the density of an atomic nucleus, what does it become? Maybe it remains mostly neutron-rich nuclear matter. Maybe heavier strange particles called hyperons appear. Maybe, in the deepest cores of the most massive neutron stars, neutrons themselves partially dissolve into quark matter, where the building blocks normally trapped inside protons and neutrons move in a more collective form. A recent review of dense neutron star matter emphasizes that observations have improved our constraints, but the equation of state, meaning the relationship between pressure, density, and internal composition, remains one of the central unsolved problems in astrophysics. This uncertainty is not weakness, it is the honest edge of knowledge. The inside of a neutron star is not a place where we can simply look and report what is there. It is more like listening to a locked room through the vibrations in its walls. When two neutron stars spiral together and merge, their gravity sends waves through space-time, and those waves carry clues about how easily the stars deform. When a pulsar suddenly spins a little faster in a glitch, it may reveal tension between the crust and deeper layers. NASA's older structural description notes that a rigid crust and a superfluid inner region may help explain such pulsar glitches, where the star's rotation jumps in a way that suggests the interior is not just a simple solid ball. Chandra observations of the young neutron star in Cassiopeia A were also interpreted as evidence that neutrons in the core can enter a superfluid-like state, a strange condition where parts of the interior move with almost no ordinary resistance, even though the star is incredibly hot by human standards. That contrast is one of the most beautiful shocks in this subject. On Earth, we usually associate such quantum smoothness with extreme cold, but in a neutron star, density is so overwhelming that matter can behave in ways that feel cold in structure while remaining unimaginably hot in temperature. Still, we must be careful. Nobody has opened a neutron star and photographed strange quark matter. Nobody has proven that every neutron star has an exotic core. The most honest scientific view is that the outer layers are better understood than the inner core, and the deeper you go, the more the star becomes a test of nature's most extreme rules. But even that uncertainty teaches you something powerful. A neutron star is not just a dead star. It is a natural laboratory built by gravity, a place where matter is pressed into forms that challenge the simple categories we learned as children. Solid, liquid, gas, metal, stone, plasma. These words become too small. The matter inside may include a crust harder than almost anything familiar, nuclear shapes arranged by forces competing at impossible density, a neutron-rich sea with quantum behavior, and perhaps, in the heaviest stars, deeper phases where the identity of particles begins to blur. And when you sit with that, the story becomes more than astronomy. It becomes a reminder that the universe hides its strangest truths, not only in distance, but in pressure. The same atoms that make your body light enough to move, breathe, and feel can, under the weight of a collapsed star, be crushed into something no hand could touch, and no ordinary language can fully hold. Matter is not one thing. It is a promise with many possible endings. In you, it becomes warmth, thought, blood, and memory. In a neutron star, it becomes a dense, silent riddle spinning in the dark, asking a question we still have not answered. When the universe squeezes reality as hard as it can without making a black hole, what is matter still allowed to be? Objects cooled almost to absolute stillness. Imagine removing heat from an object until its atoms have almost no room left to be restless, until motion itself seems to fade into a whisper, and the ordinary world begins to lose the noise that makes it feel familiar. This is the strange science of objects cooled almost to absolute stillness, and the first truth is simple but easy to misunderstand. Cold is not a substance added to matter, but the absence of thermal agitation. A hot object is not filled with some glowing invisible fluid called heat. Its atoms and molecules are vibrating, rotating, colliding, and shifting with more energy. A cold object is one where that restless motion has been reduced. Absolute zero, 0 Kelvin, is the theoretical point where ordinary thermal motion reaches its lowest possible limit, though physics does not allow us to truly reach it in practice. We can only approach it closer and closer, like walking toward a horizon that keeps its final step hidden. NIST describes absolute zero as the temperature at which atomic thermal motion would cease, while noting how laser cooling has brought atoms to incredibly tiny fractions of a degree above that point. But the journey toward near stillness is not as simple as putting something in a freezer. Your kitchen freezer slows molecular motion a little. Liquid nitrogen slows it much more. But the coldest laboratories on Earth use methods that feel almost like persuasion rather than refrigeration. Laser cooling, for example, sounds impossible at first, because lasers are usually associated with heating, cutting, and burning. Yet with the right color of laser light, atoms moving toward the beam can absorb photons in a way that gently steals some of their motion. Each interaction acts like a tiny brake, not on a car, but on a single atom drifting through space. Over many interactions, the atoms slow down dramatically. Then scientists can use magnetic or optical traps to hold them, isolate them from the warmth of the surrounding world, and sometimes use evaporative cooling, where the most energetic atoms are allowed to escape, so the remaining cloud becomes even colder. This is not just a technical achievement, it is a way of turning down the volume of matter. At room temperature, atoms are too busy for many delicate quantum behaviors to become clear. They bump, blur, and scatter like a crowd in a train station. But when cooled close to absolute zero, the crowd quiets. Patterns that were hidden by chaos begin to appear. Atoms can behave less like separate grains and more like waves with shared rules. Tiny forces become easier to detect. Clocks can become more precise. Sensors can become more sensitive. Questions about gravity, time, and quantum behavior can be asked with a gentleness that ordinary heat would normally destroy. NASA's Cold Atom Laboratory on the International Space Station was built for exactly this kind of frontier, studying ultra-cold quantum gases in microgravity, where clouds of atoms can drift longer and be examined under conditions that are difficult or impossible on Earth. And yet the deeper mystery is not only that atoms can be cooled so far, it is that stillness itself changes meaning at this scale. Even near absolute zero, matter is not perfectly frozen in the way your imagination might picture. Quantum physics leaves behind a kind of irreducible uncertainty, a lowest tremble that cannot be removed simply by cooling more. An atom near its ground state is not a dead object with no existence left inside it. It is a system pushed into its quietest allowed condition. This is why the phrase, almost absolute stillness, is more accurate than absolute stillness. Nature lets us silence thermal noise, but it does not let us erase all motion like wiping chalk from a board. There is always a final softness, a remaining quantum restlessness, as if reality refuses to become completely blank. What makes this even more astonishing is that cooling near stillness is not limited to tiny clouds of atoms. Scientists have also worked on cooling the motion of larger mechanical systems, even human-scale components, toward their quietest, measurable motion. In 2021, researchers used the extreme precision of LIGO's mirror measurements to cool the motion of a 10-kilogram object close to its motional ground state, showing that ideas once associated mainly with tiny quantum systems can reach into the world of heavy objects too. That does not mean a 10-kilogram object became a mystical frozen ghost. It means one particular kind of motion in that object was reduced to an extraordinarily quiet state. And that distinction matters because real science becomes more powerful, not less, when it is honest. Cooling objects almost to absolute stillness does not stop time. It does not create perfect nothingness. It does not make matter vanish. Instead, it reveals what matter becomes when ordinary heat no longer drowns out its smallest behavior. It shows you that the world you touch every day is loud, not only with sound, but with motion too small to see. Every table, every wall, every piece of metal, every breath of air is alive with microscopic agitation. You call it still because your eyes are too slow and your senses too broad. But to physics, stillness is rare. Stillness must be engineered. It must be protected from air, light, vibration, radiation, and even the warmth of the container meant to hold it. The closer you come to absolute zero, the more the environment becomes an enemy, because any stray energy can disturb the delicate silence you are trying to create. And maybe that is why this science feels so quietly profound. It teaches that the ordinary world is not calm. It is only calm from far away. Underneath every solid surface is motion. Underneath every cold object is remaining energy. Underneath every attempt to reach perfect stillness is a law reminding you that perfection can be approached, studied, and used, but not fully possessed. Objects cooled almost to absolute stillness are not empty of life. They are matter listening to its own deepest rules. They are what remains when heat stops shouting. They show that silence is not nothing, that quiet can be full of structure, and that sometimes, to see what reality is truly made of, you do not need to add more force, more speed, or more brightness. You need to remove the noise, lower the temperature, and wait for the hidden order of matter to finally speak. Superfluids and frictionless flow. A superfluid is a liquid that reveals what motion might look like if the world forgot how to waste energy. In ordinary life, every flow slowly dies. A river loses speed against its bed. Oil drags against metal. Air rubs against wings. And even a cup of stirred tea quietly gives up its swirl because internal friction turns organized motion into heat. This is so common that it feels like a law of existence itself. Movement fades, spinning slows, currents weaken, and everything eventually settles. But when helium-4 is cooled below its lambda point, around 217 Kelvin, part of the liquid enters a quantum state where it can flow with zero viscosity, meaning it no longer has the ordinary internal resistance that makes normal liquids lose motion. Superfluidity was first discovered in liquid helium in the 1930s, and it remains one of the clearest examples of quantum physics becoming visible at a scale you can almost imagine in a laboratory container. The important thing is to say this honestly. A superfluid is not a magical liquid that ignores all forces, and it is not a liquid that can do anything forever under any condition. It still has limits. It still responds to containers, temperature, disturbances, and flow speed. But under the right conditions, it can move in ways that ordinary liquids cannot. One of the strangest examples is persistent flow. If a superfluid is set moving around a ring-shaped path, it can continue circulating for an extremely long time without the usual slowing caused by viscosity, because there is no normal internal rubbing in the superfluid component to drain away that motion. NIST describes persistent flow in neutral superfluids as frictionless circulation in a hollow toroidal container, and similar behavior has been demonstrated in ultra-cold atomic gases. This is where the idea becomes deeper than a visual trick. Superfluid flow is not just slippery. Slippery things still lose energy. Ice is slippery, but motion across ice still fades. Oil reduces friction, but it does not erase it. A superfluid is different because its motion is tied to a shared quantum state, almost as if many particles have agreed to move according to one collective rhythm instead of behaving like separate chaotic pieces. At low enough temperature, the liquid can be described as having two interwoven parts: a normal component that carries heat and behaves more like a conventional fluid, and a superfluid component that can flow without viscosity. This two-fluid picture is a standard way physicists explain the strange mixture of ordinary and extraordinary behavior in helium-2. So when people say frictionless flow, the real meaning is not that every kind of resistance in the universe has vanished. But that one part of the liquid can move without the normal viscous drag that dominates everyday fluids. That distinction matters because the truth is more interesting than exaggeration. Superfluids also cannot rotate like ordinary liquids. If you spin a bucket of water, the whole body of water can swirl in a smooth, continuous way. But a superfluid cannot simply take on any rotation it wants. Instead, rotation appears through tiny whirlpools called quantized vortices, where circulation comes in fixed packets rather than arbitrary amounts. In superfluid helium and atomic Bose-Einstein condensates, these quantized vortices are a central feature of the flow, and they show that the liquid's motion is governed by quantum rules, not just classical fluid behavior. This is a beautiful reversal of intuition. A normal liquid can be messy in infinitely many ways, but a superfluid, even when it forms vortices, carries a kind of hidden order. Its whirlpools are not just random curls. They are marked by precise circulation. They are like fingerprints of quantum law written into motion itself. And when many of these vortices interact, the superfluid can enter quantum turbulence, a strange form of chaotic flow that is not the same as ordinary turbulence in air or water, because the swirls are built from these discrete vortex lines instead of smooth, continuous eddies. This gives superfluids a quiet double nature. They can seem impossibly smooth, yet they can also become complex in a way only quantum matter can. That is why this topic should not be reduced to liquid with no friction. The real lesson is that flow itself has hidden levels. The stream in a river, the blood in your veins, the wind around a building, and the helium inside a cryogenic lab are all forms of movement, but they are not the same kind of movement. In one world, motion constantly leaks away into heat. In another, motion can become protected by a collective state. In one world, turbulence is a storm of continuous swirls. In another, turbulence is woven from quantized threads. In one world, a liquid is a crowd. In another, it becomes closer to a single organized presence. And this should make you question what you really mean when you call matter ordinary. Maybe the familiar behavior of liquids is only what matter does when it is warm enough, noisy enough, and disordered enough to hide its deeper possibilities. Cool it down, strip away the thermal chaos, and suddenly motion becomes something else. Not just particles bumping through space, but a coordinated state that resists being broken into waste. Superfluids remind you that friction is not merely an inconvenience in machines. It is one of the ways the everyday world forgets its motion. It turns movement into heat, order into disorder, intention into fading. But in a superfluid, under rare and delicate conditions, motion can persist with a purity that feels almost philosophical. A current can keep going not because it is forced, not because energy is constantly fed into it, but because the usual pathways for losing that motion have been closed. And perhaps that is why superfluids feel so haunting. They do not just show us a strange liquid. They show us a version of movement almost untouched by decay. They suggest that beneath the noisy, dragging world we know, matter contains a quieter possibility. Flow without ordinary resistance, rotation written in quantum signatures, and motion that does not immediately surrender itself to time. Superconductors and resistance-free current. Imagine a wire carrying electricity without bleeding any of it away as heat. No fading, no warming, no slow loss in the metal, as if the current has found a hidden road where resistance simply does not exist. That is the promise of superconductors. And the first thing to understand is that they are not just very good conductors. Copper is a good conductor. Silver is even better, but both still resist the movement of electrical current. Push enough electricity through ordinary wire, and some of that energy is lost as heat, which is why power lines warm up. Electronics need cooling, and machines waste part of what we feed them. A superconductor is different because, below a certain critical temperature, its electrical resistance drops to exactly zero within measurement limits, meaning a current can keep circulating without needing a battery to constantly push it forward. This was first discovered in 1911, when Heike Kamerlingh-Onnes cooled mercury to extremely low temperatures and found that its resistance suddenly vanished. The word suddenly matters. It was not a smooth improvement, not a metal slowly getting better as it got colder, but a sharp transition into a new state of matter. One moment the material behaved like an ordinary conductor. Below the critical point, it crossed a threshold and entered a state where electricity could move in a completely different way. But the deeper secret is not only zero resistance. Superconductors also push magnetic fields out of their interior in a phenomenon called the Meissner effect. This is why a magnet can hover above a superconductor in those unforgettable demonstrations. Not because gravity has disappeared, but because the superconductor rearranges currents on its surface in a way that rejects the magnetic field and creates a stable repulsion. In some superconductors, magnetic fields can partly enter through tiny channels called vortices, and if those vortices become pinned in place by imperfections in the material, the magnet can appear locked in mid-air, floating above or even hanging below the superconductor like the space between them has become solid. It looks magical, but it is not magic. It is magnetism obeying rules that only appear when matter enters this rare electrical state. So what is happening inside? In many conventional superconductors, electrons that normally repel each other can form paired states known as Cooper pairs, helped by tiny vibrations in the crystal structure of the material. Alone, electrons scatter through a metal, bumping into imperfections and vibrations, losing energy as heat. But in a superconducting state, these paired electrons move in a shared quantum pattern that cannot easily be disrupted by the ordinary scattering that creates resistance. You do not need to picture this as little particles holding hands like characters in a cartoon. It is better to imagine a crowd that stops moving as separate individuals and begins following one perfectly coordinated rhythm, so that random collisions no longer break the flow in the usual way. This is why superconductivity feels so strange. It takes electricity, something we usually treat as practical and industrial, and reveals a hidden elegance beneath it. A current becomes not just charge moving through metal, but a collective state protected by the organization of the material itself. And yet the honesty of the science is important. Superconductors are not limitless. They only work below certain temperatures, and every superconducting material also has a critical current and critical magnetic field. Push too much current through it, expose it to too strong a magnetic field, or let it warm too much, and the superconducting state collapses. This is one reason superconductors have not replaced every wire in the world. Many of them must be cooled with liquid helium or liquid nitrogen, and cooling systems cost energy, money, and engineering complexity. High-temperature superconductors exist, but high temperature in this field can still mean far colder than anything in everyday life. Some newer materials have shown superconducting behavior at much warmer temperatures only under extreme pressures, closer to the crushing conditions deep inside planets than normal room conditions. So they are not ready to become simple household wires. The dream of a practical room temperature superconductor at ordinary pressure remains one of the great unsolved goals in materials science. Still, even with these limits, superconductors already shape the modern world in powerful ways. They are used in MRI machines, where strong superconducting magnets help doctors see inside the body without surgery. They are used in particle accelerators, where intense magnetic fields guide beams of particles around vast circular paths. They appear in sensitive scientific instruments, experimental quantum computers, powerful research magnets, and magnetic levitation systems. Their value is not only that they save energy, but that they allow magnetic fields and electrical behaviors that ordinary materials cannot sustain. They show us that resistance, something so ordinary we build our entire electrical world around managing it, is not an unavoidable property of current itself. It is a property of current moving through matter under certain conditions. Change the state of matter, and the rule changes. That is the quiet shock of superconductivity. The wire does not become empty, and the electrons do not become free in a simple sense. But the whole system reorganizes so deeply that the usual price of motion disappears. And perhaps that is why superconductors feel almost symbolic. In everyday life, Every transfer costs something. Every machine heats, every path wears down, every current meets opposition. But here, under cold and carefully protected conditions, matter reveals a rare possibility. Movement without electrical decay, magnetism sculpted into levitation, and energy traveling through a material without leaving a trail of heat behind. Superconductors do not promise a fantasy world where nothing is difficult. They remind you of something more honest and more profound. The laws you experience every day are often not the final laws of nature, but the behavior of nature under ordinary conditions. Lower the temperature, choose the right material, protect it from disturbance, and electricity begins to move as if it has remembered a cleaner language. A current can circle in silence, a magnet can hover, a machine can become possible only because resistance, for one brief and delicate state of matter, has been asked to step aside. Atoms arranged like artificial universes. What if a few thousand atoms trapped in carefully shaped light could become a tiny universe where scientists test laws that are almost impossible to watch directly in ordinary matter? This is the quiet power of atoms arranged like artificial universes. And it does not mean researchers are creating little planets, stars, galaxies, or living worlds inside a laboratory. The phrase points to something more precise and, in its own way, more astonishing. Scientists can cool atoms until their motion becomes extremely controlled, then place them inside patterns made by laser beams, forming what are called optical lattices, grids of light that act like invisible egg cartons for atoms. NIST describes optical lattices as webs of light where atoms and molecules can be trapped and used for quantum simulations, helping researchers model complex quantum processes that are hard to study directly. The atoms sit in these light-made wells, almost the way electrons sit in the repeating structure of a crystal, but with one enormous advantage. In a real solid, the atoms are packed too tightly and move too fast for you to control every detail. While in an optical lattice, researchers can tune the spacing, depth, interactions, motion, and even the shape of the entire artificial landscape. This is why these systems are often called quantum simulators. They are not ordinary computers trying to calculate every particle with brute force. They are physical systems built to behave like another physical system. Instead of asking a classical machine to imitate quantum matter from the outside, scientists build a clean, adjustable quantum world and let it reveal how such matter behaves from the inside. Reviews in Nature and Science describe ultra-cold atoms in optical lattices as powerful platforms for studying quantum many-body problems and condensed matter, systems that are difficult for conventional computers to simulate. Think of it like building a scale model of a storm, except the model is not made of plastic clouds. It is made of the same kind of hidden rules that make the real storm complicated. With optical lattices, researchers can explore questions about magnetism, insulation, conductivity, phase transitions, and the collective behavior of many particles, all inside a system that can be adjusted with a level of patience nature rarely offers. In a normal material, electrons are buried inside a solid surrounded by vibrations, defects, impurities, and complexity. You cannot simply reach in and move one part of the system while keeping everything else still. But in an artificial lattice of atoms, scientists can change one rule at a time. They can make atoms strongly interact or weakly interact. They can let them tunnel from one site to another, meaning they can move between neighboring traps in a quantum way. They can study how order appears, how it disappears, and how a calm-looking collection of particles can suddenly behave like a new kind of matter. This is not a toy universe in the childish sense. It is a controlled mirror of nature, a place where matter is simplified enough to be readable, but still real enough to be meaningful. One reason this matters is that many of the hardest questions in modern physics involve not one particle, but many particles affecting one another all at once. A single atom can be described with great precision. Two atoms are harder, but when thousands or millions begin interacting, the complexity grows so quickly that even powerful computers struggle. This is the many-body problem, and it is one of the reasons materials can surprise us. Superconductivity magnetism, strange insulating behavior, and exotic quantum phases are not always written clearly in the properties of one particle. They emerge from the crowd. They are group behaviors, and optical lattices let scientists build the crowd from the ground up. They can arrange atoms into lines, sheets, or three-dimensional structures. They can watch them with special microscopes. They can sometimes image individual sites and see patterns that would be hidden in ordinary solids. That ability changes the feeling of the science. You are no longer only guessing what the invisible particles might be doing inside a material. You are arranging a cleaner version of the material's logic and watching it unfold. And the word artificial here should not make it feel less real. Artificial does not mean fake. A violin is artificial, but the sound is real. A clock is artificial, but the time it measures is real. An optical lattice is artificial, but the quantum behavior inside it is real. It is a handmade environment where atoms obey natural laws under carefully chosen conditions. In recent years, these platforms have become advanced enough to simulate models that are central to condensed matter physics, including Hubbard-type systems, which are simplified but deeply important ways of studying how particles move and interact on a lattice. A 2025 Nature paper described neutral atom Hubbard quantum simulators as pristine realizations of such models, while also noting the continuing challenge of reaching low enough temperatures for some open problems. That honesty is important. These artificial universes are not complete answers. They are not perfect copies of every material. They have limitations: temperature, noise, system size, measurement challenges, and the difficulty of proving that a simulator truly captures every feature of the target problem. But even with those limits, they represent one of the most elegant strategies in science. When nature is too complex to calculate, build a smaller, cleaner piece of nature and ask it to behave. And maybe that is what makes this idea so quietly beautiful. We usually imagine discovery as looking outward, deeper into space, farther into the past, closer into the atom. But here discovery also means arrangement. You take neutral atoms, cool them, suspend them in light, and create a place where new behaviors can be born on command. Not fantasy worlds, not tiny galaxies, but artificial rule spaces where matter can rehearse possibilities. In one arrangement, atoms may spread freely. In another, they may lock into place. In another, they may reveal patterns similar to magnetism. In another, they may help us understand why certain materials conduct, resist, or transform. You begin to see that the universe is not only made of things, but of relationships between things. Change the spacing, change the interaction, change the allowed motion, and the same atoms begin telling a different story. That is the real wonder of atoms arranged like artificial universes. They show that reality can be studied not only by observing what already exists, but by carefully building conditions under which hidden laws become visible. A laboratory lattice of light is not a cosmos, but it is a question made physical. It asks, if we arrange matter this way, what kind of world appears? And the answer, whispered through ultra-cold atoms held in glowing patterns, is that even the smallest controlled system can become a window into rules too vast for the mind to solve alone. Bose-Einstein condensates and shared quantum states. A Bose-Einstein condensate is what happens when many separate atoms stop behaving like a crowd and begin moving as if they are one shared whisper of matter. In the ordinary world, every atom seems private. It has its own motion, its own place, its own restless path through space, and even in a quiet room, the particles around you are rushing, vibrating, colliding, and scattering too quickly for their deeper wave-like nature to become obvious. But at extremely low temperatures, when certain kinds of atoms called bosons are slowed down enough, their quantum waves spread outward until they begin to overlap, and something astonishing happens. The atoms can fall into the same lowest energy state, not as a chemical mixture, not as a frozen solid, not as a normal liquid, but as a new state of matter, where thousands or even millions of atoms behave like one coordinated quantum object. This was predicted in the 1920s after Satyendranath Bose developed a new way of thinking about particles of light, and Albert Einstein extended the idea to atoms, suggesting that under the right conditions, matter itself could condense into a shared quantum state. For decades, this remained one of those strange theoretical predictions that sounded almost too delicate to touch. Then, in 1995, researchers finally created Bose-Einstein condensates in dilute gases of ultra-cold atoms, and the achievement was so important that it later earned the Nobel Prize in Physics. But the real wonder is not just that scientists made something cold. The wonder is what cold allowed matter to reveal. In everyday life, you never see the wave nature of a baseball, a stone, or your own hand, because the waves associated with large warm objects are far too tiny and chaotic to matter in a visible way. But atoms are different. When they are cooled and trapped carefully, their wave-like behavior becomes large enough to overlap with neighboring atoms. At that point, the old picture of many tiny separate dots begins to fail. The atoms are still there, and they do not literally melt into one single atom, but they share one quantum description so strongly that the whole cloud can act like one matter wave. Imagine a choir where every singer holds the same notes so perfectly that you no longer hear individual voices, only one smooth tone filling the room. That is not a perfect analogy, because atoms are not singing and quantum states are not sound, but it gives you the feeling. Individuality does not disappear completely, yet collective behavior becomes the main story. This is why Bose-Einstein condensates feel so unsettling. They show that the boundary between one thing and many things is not always as simple as your senses suggest. A pile of sand is many grains, a flock of birds is many bodies moving together. But a Bose-Einstein condensate is more deeply unified than that, because the shared state is not just coordination from outside. It comes from the quantum rules of the particles themselves. You can make two condensates overlap, and they can create interference patterns, almost like two waves on water crossing and forming bright and dark bands. Except here, the waves are made of matter. This is one of the clearest ways to see that atoms are not merely tiny solid beads. They can spread, overlap, interfere, and behave according to probabilities that only become visible when the noise of ordinary motion is stripped away. And yet this science must be kept honest. A Bose-Einstein condensate is not a doorway to telepathy, not proof that human minds merge into one field, and not a mystical substance outside physical law. It is a real laboratory state of matter created under very precise conditions, usually involving extremely dilute gases and advanced cooling and trapping methods. It is fragile. Warm it too much, disturb it too strongly, or let it interact too chaotically with the environment, and the shared quantum order fades. That fragility is part of its beauty. It is like seeing a hidden layer of nature that exists only when the world is made quiet enough. And because it is so clean and controllable, it has become a powerful tool for studying quantum behavior. Scientists use condensates to explore matter waves, vortices, collective motion, precision measurement, and even models of more complicated systems. They can create atom lasers, where atoms emerge in a coherent beam, somewhat like light from a laser, but made of matter rather than photons. They can study how waves of atoms move through traps, how patterns form, how tiny disturbances grow, and how quantum matter behaves when many particles share one state. In that sense, a Bose-Einstein condensate is not only a strange object. It is an instrument for asking questions. It lets researchers watch quantum behavior in a form large enough to study directly, yet simple enough to control. And the philosophical pull is quiet but deep. If ordinary matter can become a shared state under the right conditions, then perhaps the world is less made of isolated things than of conditions that decide how separate things appear. The atoms in a condensate teach you that identity in physics can be contextual. Warm and restless, they behave like individuals. Cold and coordinated, they become a single quantum presence. The same ingredients, arranged under different rules, tell a different story. That is the lesson worth carrying away. Matter is not only substance, it is behavior shaped by circumstance. The universe does not always build reality from hard little pieces sitting apart from one another. Sometimes, when motion becomes quiet enough and the rules align, many pieces can enter one shared state, and the line between the individual and the collective begins to blur. A Bose-Einstein condensate is not magic. It is more humbling than magic. It is nature showing you that beneath the ordinary separateness of things, there are states where matter becomes almost musical, not because it has a soul, but because its particles have found the same quantum note and held it together in silence. Materials that bend, waves the wrong way. A beam entering a strange material can bend to the side your eyes insist should be impossible, as if the wave has crossed an invisible border where nature's usual arrows have been quietly reversed. In ordinary glass or water, you already know that waves can bend. A straw looks broken in a cup because light changes speed and direction as it enters a different medium, and sound can bend through layers of air when temperature changes. But materials that bend waves the wrong way go further than this familiar trick. They belong to the world of negative refraction, where a wave crossing into a specially designed material turns to the opposite side from what normal materials would produce. The idea was explored theoretically by Victor Veselago in the 1960s, long before engineers had materials that could actually perform it, and for years it sounded almost like a mathematical oddity, rather than something you could build in the real world. The key was not finding a magical natural substance, but designing metamaterials, artificial structures whose tiny repeating patterns are smaller than the wave they are meant to control, allowing the whole material to respond in ways ordinary chemistry usually cannot provide. Negative index metamaterials were developed because no common natural material was known to offer this kind of response across useful frequency ranges. And researchers showed that engineered structures could create electromagnetic behavior unlike conventional materials. Think of it this way: a wave does not only care what a material is made of, it also cares about the shape, spacing, and hidden architecture it meets as it passes through. If those internal patterns are arranged carefully enough, the material can make the wave's peaks, phase, and energy flow relate to one another in a deeply unusual way. In a normal material, the direction the wave appears to bend feels intuitive, like a car turning as it enters mud, or a swimmer changing direction in a current. In a negative refraction material, that intuition fails. The wave bends as though the rules of entry have been mirrored. This does not mean causality breaks, energy runs backward in time, or the wave becomes supernatural. It means the internal response of the material has been engineered so that the wave fronts and the flow of energy are arranged in a way that ordinary glass, water, and air do not show. That difference matters because the real wonder is not a law being violated. It is a law being used with such precision that the result looks like a violation to human instinct. One of the first famous demonstrations used microwaves, not visible light, because longer wavelengths are easier to control with larger engineered patterns. Later research pushed the idea toward optical frequencies using much smaller structures, but visible light negative refraction remains difficult because the patterns must be incredibly tiny and losses can become severe. This is why you should be careful with headlines. A material that bends waves the wrong way is not automatically a perfect lens, an invisibility cloak, or a portal into impossible physics. It is usually designed for a certain kind of wave over a certain frequency range under controlled conditions. The wave may be microwave radiation, infrared light, sound, vibration, or even surface waves, and each one requires its own kind of architecture. Acoustic versions can use resonators, channels, membranes, or structured materials that make sound behave as if the material has unusual effective properties. Experiments have even demonstrated negative refraction of underwater ultrasonic waves in carefully prepared acoustic metafluids. This is where the topic becomes larger than light. Bending the wrong way is really a lesson about how waves read the world. A wave does not see a wall, a lens, or a material the way you do. It feels delay, response, spacing, reflection, resonance, and allowed paths. Build the right microscopic or mesoscopic pattern, and you can make the wave behave as if it is traveling through a medium with properties nature did not conveniently hand you. That is the quiet revolution of metamaterials. Instead of accepting the properties of matter as fixed gifts, scientists begin to write new wave rules into structure itself. Negative refraction has also inspired the idea of a perfect lens, because ordinary lenses lose some of the finest details of an object, especially information carried by rapidly fading near-field waves. Theoretical work by John Pendry suggested that a negative index slab could, in principle, recover some of that lost detail and beat ordinary imaging limits, though real materials bring practical obstacles such as absorption, limited bandwidth, and fabrication difficulty. So the honest story is not that we have a universal lens that sees everything perfectly. The honest story is that the direction a wave bends is not as sacred as it seems. Under the right engineered conditions, waves can be guided into behaviors that feel backwards, and that backwardness can reveal new ways to image, sense, filter, guide, and manipulate signals. Imagine designing a material not by asking, "What is it made of?" but by asking, "What journey do I want a wave to experience inside it?" That is a profound shift. It turns matter into a landscape for waves. A landscape where roads can slope the wrong way, mirrors can be flattened into slabs, and direction itself can become a design choice. And perhaps that is why this science stays in the mind. It reminds you that your sense of normal is trained by the narrow materials you meet every day. Glass bends light one way, water bends it another, air barely bends it at all, and from that small sample you build an intuition about reality. But the universe is not limited to your intuition. When humans learn to arrange matter at scales waves can feel, the familiar rules begin to open like hidden doors. A wave that once seemed forced to turn right can be made to turn left. A material that looks passive can become an active map of delays and responses. And what looked like the wrong way may simply be a deeper way, waiting for matter to be built with enough care to show it. Twisted graphene and magic angle physics. A sheet of graphene is already strange, but twist two sheets by just over 1 degree, and the material begins acting as if a hidden dial inside reality has been turned. Graphene itself is only 1 atom thick, a flat honeycomb of carbon atoms so thin it almost feels like a mathematical surface made physical. Yet it is strong, conductive, flexible, and deeply unusual in the way its electrons move. For years, that was already enough to make it one of the most studied materials in the world. But then researchers found that if you stack 2 graphene sheets and rotate one very slightly against the other, something new appears. Not because the carbon atoms change, and not because a new element is added, but because the 2 atomic patterns interfere with each other and create a much larger repeating design called a moiré pattern. You have seen a simple version of this effect before, maybe when 2 window screens overlap and slow waves of dark and light suddenly appear, even though each screen is perfectly regular by itself. In twisted graphene, that larger pattern is not just visual decoration. It changes how electrons experience the material. At most twist angles, the electrons still move in ways that are interesting but not completely shocking. Yet near a special angle of about 1.1 degrees, now famous as the first magic angle, the electronic energy bands become unusually flat, meaning the electrons lose much of their usual freedom to rush through the material, and their interactions with one another become far more important. This is where the story becomes extraordinary. In 2018, experiments from Pablo Jarillo Herrero's group at MIT showed that magic angle twisted bilayer graphene could become a correlated insulator under certain conditions. And then, when the electron density was tuned, it could also show superconducting behavior at very low temperatures. That does not mean 2 pieces of carbon tape suddenly become a room temperature miracle device, and it does not mean every twisted graphene sample behaves perfectly. The effects are delicate. The angle must be controlled with remarkable precision. The sample must be extremely clean. The temperatures are very low. Small disorder, strain, pressure, and alignment can change the outcome. But that fragility is exactly what makes the discovery feel so important. It shows that in some materials, geometry alone can act like a powerful control knob. You are not changing the recipe of matter, you are changing the relationship between its layers. You rotate one sheet almost imperceptibly, and the electrons begin to live in a new landscape. This is why the field is sometimes called twistronics, because twisting becomes a way of engineering electronic behavior. Instead of only asking what a material is made of, scientists can now ask how its layers are arranged, how they are rotated, how strongly they talk to each other, and how electrons move through the large moire landscape that emerges. That idea opens a new kind of materials science, one where stacking and twisting two-dimensional crystals can create properties that neither layer has alone. And what makes magic angle graphene especially fascinating is not simply that it can superconduct, but that it sits near other unusual states, including insulating behavior that appears even though the material might seem like it should conduct. In ordinary thinking, an insulator blocks current because electrons are stuck by the material's basic structure. But in correlated materials, electrons can block each other through their own collective behavior. Like people in a narrow hallway who cannot move freely because everyone is in everyone else's way. Magic angle graphene gives researchers an unusually clean, tunable way to study that kind of collective electronic life. By applying electric gates, scientists can add or remove electrons without chemically changing the material, almost like adjusting the population of a tiny electronic city and watching whether it becomes quiet, flowing, resistant, or strangely ordered. Later work has continued to reveal how rich this platform is, with measurements aimed at understanding the nature of its superconductivity and related moire states, including recent studies that directly probe properties such as superfluid stiffness in magic angle graphene systems. But the central mystery remains open. Why exactly do these electrons pair and organize the way they do? And how much of it resembles other unconventional superconductors that physicists still do not fully understand? Some research points towards strong electron interactions. Some explores the role of vibrations in the lattice. Some studies how the moire pattern reshapes the electronic bands. The point is not that the final answer has already been found, but that twisted graphene gives scientists a tabletop arena where difficult questions about quantum materials can be tuned, repeated, and tested with rare control. And this is where the topic becomes more than a material fact. It changes how you think about small changes. A twist of about 1 degree sounds almost meaningless in everyday life. You would barely notice it in a book on a table, a picture frame on a wall, or a sheet of paper turned slightly in your hand. But at the atomic scale, that tiny rotation creates a new world for electrons. It builds a hidden super pattern larger than the original atomic grid, and that pattern changes what the material can become. There is something quietly humbling in that. Matter is not only transformed by heat, pressure, chemistry, or extreme forces. Sometimes it is transformed by alignment, by angle, by the relationship between two nearly identical layers. The same carbon, placed differently, begins to tell a different story. And maybe that is the deeper lesson of magic angle physics. Reality does not always need a dramatic ingredient to become strange. Sometimes the universe only needs a slight misalignment, a nearly invisible turn, a small geometric shift that lets hidden behavior rise to the surface. Twisted graphene is not magic in the supernatural sense. It is more interesting than that. It is a material that shows how delicate the boundary can be between ordinary conduction, blocked motion, and collective quantum order. It reminds you that the deepest properties of matter may not live only inside the atom, but also in the pattern between atoms, the angle between layers, and the quiet geometry of how one piece of reality is placed upon another. Why matter has more phases than school ever taught. School makes matter sound simple, as if the universe only gives you 3 basic masks: solid, liquid, and gas. But the deeper you look, the more you realize that matter has an entire hidden wardrobe. A solid holds its shape, a liquid flows, a gas expands, and that early lesson is useful because it gives your mind something stable to begin with. But it is not the full story. It is the doorway. Matter does not only change because it melts, freezes, boils, or condenses, it can also reorganize its internal order, its electrical behavior, its magnetic behavior, its quantum behavior, and even the way its particles cooperate with one another. A phase of matter is not just about what something looks like to your eyes. It is about the pattern of behavior inside it. Ice and liquid water feel different because their molecules are arranged differently and move differently, but the same idea goes much further than water. Iron, for example, can become magnetic when many tiny magnetic moments inside it line up together, and then lose that magnetism when heat disrupts the order. That magnetic state is also a kind of phase, even though the iron may still look solid before and after. Some materials can be electrically insulating in one condition and conducting in another. Some can become superconducting, where electrical resistance disappears under specific conditions. Some can form liquid crystals, which flow like liquids but keep a partial inner order like crystals, making them useful in display technology. Some substances become plasma, where atoms are stripped into charged particles, and the material begins responding strongly to electric and magnetic fields, as in lightning, neon signs, and the outer layers of stars. And then there are stranger phases that do not fit ordinary classroom categories at all. Topological phases, where the important feature is not only local arrangement, but a deeper global property. Supersolids, where matter can show signs of crystalline order, while also behaving with superfluid-like flow. Quantum spin liquids, where magnetic moments refuse to freeze into a simple pattern, even at extremely low temperatures. And quark gluon plasma, a hot, dense state thought to have existed just after the Big Bang and briefly recreated in particle collisions. None of these are fantasy labels. They are attempts to describe real behaviors that appear when matter is pushed into unusual conditions or arranged in unusual ways. The reason school usually starts with solid, liquid, and gas is not because nature stops there, but because human learning needs a simple map before it can face the real landscape. The deeper truth is that matter has phases the way music has moods. A piano has the same keys, but different arrangements can become a lullaby, a warning, a memory, or a storm. Matter also uses the same particles in different patterns. Carbon can become soft graphite, hard diamond, or a one-atom thick sheet called graphene, not because carbon changed its identity, but because its bonds and structure changed the behavior that emerged. Water can become many forms of ice under different pressures, some with crystal structures that never appear in your freezer. Helium can enter states so unusual that it flows in ways ordinary liquids cannot. Metals can suddenly change their structure when heated or cooled, reshaping their strength, flexibility, and memory. This is why modern physics and materials science do not treat phases as a short school list, but as a vast catalogue of possible order. What matters is not only whether particles are close together or far apart, but whether they are arranged regularly, whether they can move freely, whether their spins align, whether their waves overlap, whether electrons are locked or mobile, whether symmetry is broken, and whether hidden patterns protect certain behaviors. You do not need heavy symbols to understand the feeling of this. Imagine a crowd in a city square. If everyone stands still in rows, the crowd behaves one way. If everyone wanders freely, it behaves another. If everyone begins marching together, another pattern appears. If small groups form, if traffic lanes open, if everyone suddenly follows a shared rhythm, the same people create completely different collective states. Matter is similar. Atoms are not just tiny pieces sitting there. Together they can form organized behaviors that no single atom could show alone. This is called emergence, and it is one of the most important ideas behind why matter has so many phases. A single water molecule is not wet. A single iron atom is not a horseshoe magnet. A single carbon atom is not diamond. The phase appears when many pieces interact, and a larger pattern becomes real. That is why matter can still surprise us. Scientists can discover new phases not by inventing new particles, but by cooling materials, compressing them, layering them, twisting them, magnetizing them, shining light on them, or placing them in carefully controlled fields. Each condition asks matter a different question. and matter answers with a different behavior. This should change the way you see the objects around you. A table is not just solid. It is matter currently living in one stable arrangement among many possible arrangements. A screen is not just glass and electronics. It depends on liquid crystals, semiconductors, and controlled phases of charge and light. The sun is not just hot gas. Much of it is plasma, a state where charged particles flow under magnetic forces. Even your body depends on phase behavior. Membranes, proteins, water, fats, and minerals all work because matter can organize itself into structures with specific properties. So the childhood list was never wrong. It was simply too small. Solid, liquid, and gas are like the first three colors someone teaches you before you discover that the world contains shades, gradients, and forms of light you cannot even see. Matter has more phases than school ever taught because nature is not organized for simplicity. It is organized by possibility. Change the temperature, pressure, structure, interaction, or collective order, and the same basic ingredients can become something new. And maybe that is the quiet lesson hidden inside the science. Reality is not only made of things, but of arrangements. What something is depends on how its parts relate, how they move, how they cooperate, and what conditions surround them. Matter is not a fixed answer. It is a set of possible behaviors waiting for the right environment to reveal them. And the more we learn, the more the ordinary world begins to look less like a finished object and more like a library of phases, most of which we were never taught to read. Metamaterials and negative refraction. A metamaterial is not strange because of what it is made from, but because of the secret instructions hidden in its shape. Take a normal material like glass, metal, plastic, or ceramic, and its behavior is mostly controlled by the atoms and molecules inside it. But a metamaterial is different. It is designed like an artificial landscape for waves, built with tiny patterns, rings, gaps, layers, or repeating structures that are often smaller than the wave passing through them. To your eye, it may look like an ordinary slab or surface, but to light, sound, heat, or microwaves, it can feel like a maze with rules that do not exist in natural materials. This is where negative refraction becomes one of the most fascinating ideas in modern physics. Normally, when light enters water or glass, it bends in a predictable direction because its speed changes inside the material. That is why a spoon in a glass of water looks broken and why lenses can focus light. But in a negative refraction material, the wave bends to the opposite side from what your intuition expects, not because physics is being broken, but because the material has been engineered so carefully that the wave's internal rhythm is guided in an unusual way. The material does not simply slow the wave or block it. It reshapes the relationship between the wave's direction, energy flow, and internal oscillation. This sounds abstract, but the idea is simple enough to feel. Imagine walking into a room where every floor tile quietly redirects your steps, so that even though you think you are moving forward, the room itself is guiding you along a path your body would never choose on its own. A metamaterial does something similar to waves. It tells them how to behave through structure. The first practical demonstrations worked with microwaves, because microwaves have longer wavelengths and can be controlled with larger, easier to build patterns. Visible light is far harder because its waves are much smaller, requiring structures so tiny and precise that fabrication becomes extremely difficult. This is why real negative refraction metamaterials are not universal miracle objects. They do not work for every color, every direction, every size, or every situation. Many operate only over narrow frequency ranges. Some lose energy as waves pass through them. Some are difficult to scale up. But these limits do not make them less important. They make the real achievement clearer. Scientists have learned that material properties are not only discovered in nature, they can be designed. Before metamaterials, you might think of a material as something you find, mine, grow, melt, or refine. After metamaterials, a material becomes something you can write, almost like a physical sentence that waves know how to read. This has changed how researchers think about lenses, antennas, sensors, sound control, heat flow, vibration shielding, and even imaging systems. Negative refraction is especially powerful because it suggested, in theory, that a flat slab could focus waves in a way ordinary lenses cannot, potentially recovering details that normal optics usually lose. In practice, building such perfect systems is extremely hard, but the idea pushed science into a new territory. Instead of asking only how to make clearer glass or stronger metal, we began asking how to sculpt the path of waves themselves. And the deeper lesson is not limited to light. Metamaterial principles can be applied to sound, where engineered structures can guide acoustic waves, to mechanical vibrations, where patterns can block or redirect motion, and to thermal systems, where heat flow can be shaped in unusual ways. Each case has its own rules, but the philosophy is the same. The wave does not only respond to substance, it responds to architecture. That is what makes metamaterials feel almost philosophical. They remind you that the behavior of matter is not always trapped inside the material's chemical identity. Sometimes the pattern is the power. The same base ingredients, arranged differently, can create entirely different responses. A sheet with the right microscopic design can act unlike the raw substance it is made from. A structure can become more important than composition, and this should change how you see the world around you. You are surrounded by objects that look passive, but every surface is already negotiating with waves. Light reflecting from paint, sound bouncing from walls, heat leaking through windows, radio signals passing through air, vibrations traveling through floors. Metamaterials take that negotiation and make it deliberate. They turn the hidden conversation between waves and matter into an engineered language. Negative refraction is one of the most dramatic sentences in that language, because it tells a wave to bend in a direction that feels wrong to human instinct, yet perfectly legal to physics. So the wonder here is not that scientists found a loophole in reality. The wonder is that reality was always richer than the natural materials around us suggested. Nature gave us glass, water, crystal, metal, and air, and from them we learned a small grammar of how waves move. But metamaterials show that the grammar can be extended. New rules can be built. New paths can be written into matter. And once you understand that, material no longer means just something you hold in your hand. It becomes a designed environment for forces, signals, and waves. It becomes proof that sometimes the strangest properties do not come from discovering a new substance, but from arranging ordinary substance with extraordinary precision until the wave entering it meets a world where the expected direction is no longer the only direction available. Graphene and one-atom-thick strength. A material thinner than anything your eyes can truly imagine can be strong enough to make steel feel almost clumsy by comparison. Graphene sounds impossible the first time you hear it. A sheet of carbon, only one atom thick, arranged in a flat honeycomb pattern, so thin that calling it a sheet almost feels generous, and yet so mechanically remarkable that it became one of the most famous materials in modern science. The Nobel Prize in Physics 2010 was awarded to Andrei Geim and Konstantin Novoselov for their groundbreaking experiments with graphene, described by the Nobel Committee as a thin flake of ordinary carbon, just one atom thick with exceptional properties rooted in quantum physics. But the strange part is not only that graphene is thin. Many things can be thin and fragile. A soap bubble is thin. A film of oil on water is thin. A sheet of dust is thin. Graphene is different because its thinness does not come with weakness in the way your intuition expects. Each carbon atom in graphene is bonded to 3 neighbors in a tight repeating pattern, and that pattern spreads strength across the sheet like a net where every knot helps hold the next. Instead of thickness giving it power, connection gives it power. This is why graphene is often described as one of the strongest materials ever measured at the microscopic scale, while also being lightweight, flexible, electrically conductive, thermally conductive, and nearly transparent. The University of Manchester notes that graphene is many times stronger than steel, incredibly lightweight and flexible, and conductive while still transparent. That combination is what made the world pay attention. Usually materials force trade-offs. Something strong may be heavy, something transparent may be fragile. Something conductive may not be flexible. Something thin may tear easily. But graphene seems to gather qualities that do not usually sit together in one material, as if carbon discovered a way to become both skeleton and skin, wire and window, surface and strength. And yet the truth must stay honest. Graphene is not a magic blanket you can simply stretch over a bridge and make it indestructible. And it is not already replacing steel in every building, battery, phone, airplane or computer chip. The strongest claims often refer to extremely clean, nearly perfect graphene measured under controlled conditions. Real-world graphene is hard to manufacture at large scale without defects, wrinkles, grain boundaries, contamination, or weak contact with other materials. A single missing atom, a tear, a chemical impurity, or a poorly connected boundary can change how the sheet behaves. Research on mechanically exfoliated monolayer graphene notes that strength can drop significantly in larger flakes, and that defects can act like weak points, lowering performance compared with ideal values. So the real lesson is more subtle and more useful than the hype. Graphene shows what matter can do when structure is almost perfectly arranged, but it also shows how unforgiving perfection can be. At 1 atom thick, there is no hidden interior to protect it. Every atom is surface. Every defect matters. Every edge is exposed. This makes graphene powerful, but also delicate in the practical sense, because building with it requires not only making the material, but preserving its quality, connecting it to other materials, layering it, transferring it, patterning it, and doing all of that without destroying the very properties that make it special. That is why graphene's future is not one single miracle product, but many possible uses, each with its own difficulties. It may strengthen composites when mixed carefully with polymers or other materials. It may help create flexible electronics, transparent conductive films, sensitive sensors, advanced membranes, heat-spreading layers, coatings, and improved energy storage components. It may matter in places where being thin, conductive, strong, and responsive is more important than replacing a giant steel beam. And perhaps that is where graphene becomes most interesting. Not as a fantasy supermaterial that solves everything, but as a new kind of platform, a reminder that the properties of matter can change radically when you reduce it to a nearly pure two-dimensional form. A block of graphite, like the lead in a pencil, is made of stacked carbon layers that slide over one another easily, leaving dark marks on paper. But isolate one single layer from that stack, and suddenly the same carbon becomes a material that can carry electrons with unusual efficiency, bend without simply snapping, absorb only a small fraction of visible light, and hold itself together with extraordinary strength. The ingredient did not change. The arrangement changed. The dimension changed. The behavior changed. That should make you pause, because it means the world is not only built from substances, but from architecture at scales too small to see. Carbon in one arrangement becomes soft graphite. Carbon in another becomes diamond. Carbon in one flat atomic layer becomes graphene. The identity of matter is not just what atoms are here, but how are they connected and how much freedom do they have? This is why graphene feels almost philosophical without needing exaggeration. It is a material that teaches humility. It shows that strength does not always come from bulk. Sometimes strength comes from precision. Sometimes the thinnest thing in the room can carry the most surprising resilience. And it also teaches patience, because turning a scientific wonder into reliable technology is slower than headlines suggest. Discovery is only the first door. Manufacturing, safety, cost, durability, integration, and quality control are the long hallway after it. Still, the wonder remains real. A single atomic layer of carbon helped open the modern world of two-dimensional materials, where scientists now explore not only graphene but many other ultra-thin crystals, each with different electronic, optical, and mechanical personalities. Before graphene, the idea of a stable, isolated, one-atom-thick material seemed almost unreasonable to many people. After graphene, it became a whole field. And maybe that is the quiet ending hidden inside this sheet of carbon. Matter does not have to be large to be powerful, and the strongest structures are not always the ones that look massive from the outside. Sometimes, Nature hides strength in a pattern so thin it is almost invisible. A honeycomb of atoms lying flat like a silent page, waiting for human hands to learn how to read it without tearing it. Ferrofluids and magnetic liquids. A ferrofluid looks like black ink until a magnet approaches, and then the liquid suddenly grows spikes, ridges, and living-looking shapes, as if the invisible force around it has become visible for a moment. The truth behind this is not magic, not alien matter, and not a liquid metal being pulled like melted iron. A ferrofluid is usually a carrier liquid filled with extremely tiny magnetic particles, often iron oxide particles so small that they remain suspended instead of sinking like sand in water. Each particle is coated with a surfactant, a kind of protective molecular layer that helps stop the particles from clumping together, while random thermal motion helps keep the nanoparticles dispersed throughout the liquid rather than settling at the bottom. In the absence of a magnetic field, the tiny magnetic directions inside the fluid are usually scattered and random, so the liquid may look calm, dark, and ordinary. But when a magnet is brought close, those particles respond together, and the whole liquid begins to behave as if it can feel the shape of the magnetic field around it. That is why ferrofluids are so visually hypnotic. They turn something normally invisible into movement, texture, and form. Magnetic fields are always there around magnets, but you cannot see them directly. With iron filings on paper, you can glimpse their lines in a flat, dry pattern. With a ferrofluid, the field becomes three-dimensional and alive-looking, because the liquid surface rises into peaks where magnetic forces pull upward while gravity and surface tension try to pull the fluid back down. This spiky pattern is called the Rosenzweig instability, a real physical effect in which a flat ferrofluid surface becomes unstable under a strong enough magnetic field and organizes itself into repeated peaks. Researchers describe ferrofluids as stable colloidal suspensions of magnetic nanoparticles, with surfactants preventing aggregation and Brownian motion helping keep particles from settling, while studies of ferrofluid spikes connect these patterns to the Rosenzweig instability at fluid interfaces. What makes this even more interesting is that ferrofluids were not invented just to make mesmerizing videos. Their history reaches back to space engineering. NASA explains that in the early 1960s, Stephen Papel worked on a magnetic liquid concept for rocket fuel, suspending finely ground iron oxide particles in fuel, so an electromagnet could pull the liquid toward an engine intake in zero gravity, where ordinary fuel might float away from where it needed to be. The original rocket fuel idea did not become the main way ferrofluids changed technology, but it opened a path into many practical uses. Today, ferrofluids can be used in seals, especially in rotating shafts, where a magnetic field holds the liquid in place to block dust or gas. They can help cool or damp motion in some speaker systems, where the fluid sits near the voice coil and improves heat transfer while also affecting movement. They have been explored in medical research, sensors, optics, art, and precision devices, though each use requires careful design because ferrofluids are messy, staining, chemically specific, and limited by the carrier liquid. Temperature, particle stability, and magnetic strength. This honesty matters because ferrofluids are often shown online as if they are liquid robots or programmable living matter. They are not alive. They are not thinking. They are not obeying the magnet like a creature obeying a command. What you are seeing is a competition of forces. Magnetism pulling the particles, surface tension trying to smooth the liquid, gravity pulling it down, viscosity resisting motion, and the chemistry of the suspension, keeping the particles separated enough for the fluid to remain fluid. The beauty comes from balance. If the particles were too large, they would settle. If they were not coated, they would clump. If the magnetic field were too weak, the surface would stay flat. If it were too strong or poorly controlled, the fluid might smear, jump, or stick in unwanted ways. Ferrofluids are fascinating because they sit at the border between liquid and field, chemistry and motion, order and instability. They show that a material does not need to be solid to respond to invisible structure. It can flow and still organize. It can look chaotic and still follow precise physical rules. And when those sharp black peaks rise toward a magnet, what you are really seeing is not the liquid choosing a shape, but nature solving a problem in real time. Where can the surface go so the magnetic energy, gravity, and surface tension reach a new balance? That is why the shapes appear so clean, almost architectural. The field writes pressure into the fluid, and the fluid answers with geometry. There is something deeply instructive in that. Most of the forces shaping your world do not announce themselves visually. Gravity does not glow. Magnetism does not have color. Air pressure does not draw lines in space. But under the right conditions, matter can become a translator. A compass needle translates Earth's magnetic field into direction. A flame translates air currents into flicker. A ferrofluid translates magnetic force into spikes, waves, and motion. It does not create the invisible. It reveals it. And maybe that is why ferrofluids feel so strangely alive when they move. They remind you that reality is full of hidden fields pressing quietly through ordinary things, waiting for the right material to make them visible. A drop of ferrofluid is not just black liquid under a magnet. It is a dark mirror for an unseen force, a small pool where invisible geometry rises into touchable form, and for a moment, the world lets you watch a force field draw itself in matter. Non-Newtonian fluids under stress. Punch a bowl of the right liquid, and instead of splashing away, it can hit back like a solid surface that only exists for the instant you attack it. This is the strange world of non-Newtonian fluids under stress, where matter refuses to stay in the neat category your eyes assign to it. A normal liquid, like water, behaves in a fairly predictable way. Stir it gently or stir it harder, and while the motion changes, the liquid's basic resistance to flow stays roughly the same. That is why water pours like water whether you tilt the glass slowly or quickly. But non-Newtonian fluids do not follow that simple rule. Their thickness can change depending on how they are pushed, pulled, squeezed, stirred, or struck. Some become thinner when you force them to move, like ketchup finally sliding out of a bottle after you shake or squeeze it. Some become thicker when stressed, like a mixture of cornstarch and water, often called oobleck, which can flow through your fingers when handled gently, but stiffen dramatically when hit. The fascinating part is that it is not switching permanently from liquid to solid like water freezing into ice. It is responding to stress in real time. The same material can feel soft when treated slowly and rigid when treated suddenly, as if it is listening not only to what you do, but to how fast and how violently you do it. To understand this without turning it into fantasy, picture the fluid not as one smooth substance, but as countless tiny particles suspended in liquid. When you move gently, those particles have time to slide past one another, with the liquid between them acting like a cushion. The mixture flows. But when you strike it quickly, the particles are forced together faster than the liquid can move out of the way smoothly. They crowd, jam, and press into temporary networks of contact, almost like a crowd of people trying to rush through a narrow door all at once. The result is a sudden resistance, a short-lived solid-like response created not by freezing, but by jamming. This is why you can sometimes run across a pool of cornstarch mixture if you keep moving quickly, but sink if you stop. Each fast step creates enough stress to stiffen the material beneath your foot for a moment. Stand still and the stress fades. The particle network relaxes and the mixture flows again. That detail is important because it keeps the science honest. Non-Newtonian fluids are not magical armor by themselves, and oobleck is not a perfect shield. Its behavior depends on concentration, particle size, liquid content, container shape, temperature, impact speed, and how confined the mixture is. If there is too much water, it flows too easily. If it dries out, it becomes a crumbly paste. If the stress is applied in the wrong way, it may not stiffen as expected. But under the right conditions, the behavior is real, dramatic, and useful. Engineers study shear thickening fluids because they can absorb energy during sudden impacts, reduce vibration, and potentially improve protective materials when combined properly with fabrics or structures. The idea is not that a liquid alone replaces steel, but that a flexible material treated with a shear thickening fluid might remain comfortable during normal movement and become more resistant during a sharp impact. That possibility is powerful because it suggests protection does not always have to be rigid all the time. It can be responsive. It can be soft until the moment it needs to harden. And that idea reaches beyond armor. Non-Newtonian behavior matters in food, cosmetics, medicine, construction, manufacturing, and biology. Toothpaste must stay in place on a brush, but flow when squeezed from a tube. Paint should spread under a brush, but not drip too easily down a wall. Blood is not a simple liquid either. Its flow changes through vessels of different sizes and under different conditions. Mud, lava, quicksand, shampoo, creams, gels, and industrial slurries all remind us that liquid is not one behavior, but a wide family of possible responses. The world you touch is full of substances that behave one way under patience and another under pressure. That is what makes non-Newtonian fluids so satisfying to watch and so useful to study. They make visible a truth that is usually hidden inside equations and factories. Matter is not always defined only by what it is. Sometimes it is defined by what is happening to it. A cornstarch mixture at rest is not the same experience as that same mixture under sudden force. A material in slow flow is not the same as a material under impact. Stress becomes part of the identity, and perhaps that is why this science feels strangely personal without needing to become metaphor-heavy. You learn that resistance can appear only when pressure arrives. You learn that softness and strength are not always opposites. You learn that the boundary between liquid and solid can be less like a wall and more like a reaction. Non-Newtonian fluids do not break the rules of matter. They reveal that the rules are more conditional than school made them seem. They teach that flow can be intelligent-looking without being alive, responsive without having intention, and surprising without being false. When you slowly dip your hand into oobleck, it opens around you. When you punch it, it refuses. The material has no mind, no choice, no hidden will. It is simply obeying the physics of particles, liquid, confinement, and force. But in that obedience, it gives you one of the clearest lessons in materials science. The same substance can become different under stress, and sometimes the most interesting thing about matter is not how it behaves when the world is gentle, but what it becomes when the pressure suddenly arrives, metals that remember their original shape. Bend a certain metal out of shape, heat it gently, and it can return to its old form, as if the object has been carrying a quiet memory inside its bones. This is the strange behavior of shape memory metals, and the first thing to understand is that the metal is not remembering in the way a mind remembers. There is no awareness inside it, no tiny intelligence deciding where to go back, no ghost of its former shape pulling it home. The memory is physical. It is stored in the way the atoms are arranged, in the internal structure of the alloy, and in a reversible transformation that can happen when temperature changes. The most famous example is nitinol, an alloy made mainly from nickel and titanium, and it can be trained into a shape at high temperature, cooled, bent into a different form, and then heated again until it returns to the trained shape. To someone watching for the first time, it can look almost impossible. A twisted wire straightens itself, a bent strip curls back, a crushed frame rises into a previous geometry. But the metal is not breaking the rules of physics. It is following a deeper set of rules than ordinary metal usually shows you. Most metals, when bent too far, stay bent because their internal crystal structure has been permanently rearranged by defects sliding through it. You take a paperclip, bend it back and forth, and eventually it weakens or snaps. Its shape change is damage accumulating, but in a shape memory alloy, part of the deformation can happen through a different mechanism. At lower temperature, the metal may be in a phase called martensite, where the atomic structure can shift between slightly different internal variants. When you bend it, you are not simply tearing the structure apart. You are often rearranging these variants like folding a set of microscopic tiles. Then, when heat is added, the alloy changes back into a higher temperature phase called austenite, and that phase carries the geometry that was originally trained into the material. The metal returns, not because it chooses to, but because the lower energy arrangement at that temperature demands that return. It is memory without consciousness, memory written as architecture. That idea alone should make you look differently at the word solid. A solid feels fixed, stubborn, final. But inside many solids, atoms are not locked in one simple pose forever. They can shift collectively, reorganize, and cross thresholds where a material suddenly becomes something else, while still looking like the same object from the outside. Shape memory metals reveal that a solid can hide more than strength. It can hide instructions. It can hold a preferred form, lose it temporarily, and recover it when the right signal arrives. In this case, the signal is often heat, though some shape memory behavior can also be triggered or assisted by stress, magnetic effects, or other conditions in more specialized materials. The practical uses are as interesting as the phenomenon itself. Nitinol is used in medical devices because it can be compressed into a small shape and then expand inside the body when warmed, which is useful for certain stents and implants. It can be used in eyeglass frames that bend and spring back. It can be used in tiny actuators, couplings, valves, orthodontic wires, and devices where a small change in temperature needs to create movement without a motor. NASA has also explored shape memory alloys for aerospace systems, where metals that move with temperature could help reduce mechanical complexity or improve aircraft efficiency. But this is not a miracle material that can repair any damage or remember any shape forever. The truth is more careful. Shape memory alloys work only within design temperature ranges. Their recovery depends on composition, heat treatment, training, strain limits, and how many times they are cycled. Bend them too far, overheat them, fatigue them through repeated use, or damage their internal structure, and the memory can degrade. They can produce useful force, but they are not infinitely strong. They can move without traditional motors, but they can be slower because heating and cooling take time. They are powerful precisely because they are conditional. Their wonder lives inside limits, and those limits are what make them real. A shape memory metal does not tell you that matter is magical. It tells you matter is programmable in ways that once seemed magical. By choosing the right alloy composition and thermal treatment, engineers can set transformation temperatures and shape response. They are not commanding atoms individually like tiny workers, but they are shaping the landscape of possibilities inside the metal so that, when heat arrives, the material follows a prepared path back to a chosen form. Imagine a road that disappears under snow. You may not see it, but when the snow melts, the shape of the land guides the water into the old channel. In a shape memory metal, the train structure is something like that hidden channel. The visible object may be bent, folded, or distorted, but the internal phase transformation knows the route back. This changes the emotional feel of material science. We often think of technology as adding more parts. Motors, hinges, wires, batteries, gears, sensors. Shape memory alloys suggest another possibility. What if the material itself can do some of the moving? What if motion can be built into the substance, not attached afterward? A spring stores mechanical energy, but a shape memory alloy can store a preferred geometry and release movement through heat. That turns matter from passive material into active participant. It becomes not just something a machine is made from, but something that behaves like part of the machine. And perhaps that is why these metals are so fascinating to watch. They blur the line between object and action. A normal wire simply sits there until a force moves it. A shape memory wire can contract when heated, like a silent muscle made of metal. A normal frame stays bent after stress. A shape memory frame can recover if the deformation stays within its designed range. The metal is still dead matter, but it behaves with a kind of stored intention that makes it feel alive for a moment. And that feeling, if you examine it honestly, comes from our surprise at learning how much structure can matter. The atoms are not random. The phases are not meaningless. The transition is not decoration. The memory is the material's internal story returning to its earlier chapter when the temperature turns the page. So when you see a bent piece of nitinol straighten in warm water, do not think of it as a trick. Think of it as a lesson about what matter can carry. A shape can be more than a temporary outline. Under the right conditions, it can be a state the material is waiting to recover. And in that quiet return, there is a deeper question. How many objects around you seem lifeless, only because you have never learned the signal that would wake their hidden behavior? A metal that remembers its shape does not have a mind, but it does have a past written into its structure. And when heat reaches it, that past becomes motion, shape memory alloys, and material memory. A shape memory alloy does not remember like a living mind, yet it can be trained so deeply that heat, pressure, and time seem to call its old body back from hiding. This is one of the most quietly unsettling ideas in materials science. A metal can carry a programmed response inside its structure, not as a memory stored in nerves or thought, but as a reversible arrangement of atoms waiting for the right condition to return. In ordinary life, when you bend metal, the change feels final. A dented spoon stays dented, a twisted wire stays twisted. A crushed piece of metal may be repaired by force, but it does not normally rise back into its earlier shape on its own. Shape memory alloys are different because their deformation can be linked to a phase change inside the solid itself. They are not simply elastic like rubber, and they are not simply hard like steel. They live in a stranger middle ground, where the same material can act soft and reconfigurable in one state, then stronger and shape recovering in another. The most famous family is nickel-titanium alloy, often called nitinol. But the deeper idea reaches beyond one name. Certain alloys can switch between two internal crystal arrangements, and that switch gives them the ability to recover large shape changes when heated or unloaded. One mode is the classic shape memory effect, where the alloy is deformed in its lower temperature state and then returns toward a trained form when warmed. Another mode is superelasticity, where the alloy can bend or stretch far more than a normal metal and spring back when the force is removed, because stress itself triggers the internal transformation and then releases it. This is not ordinary springiness. A normal spring stores energy by being stretched within its elastic range, but if you push it too far, it permanently deforms. A superelastic shape memory alloy can survive larger reversible strains, because the material is not merely stretching atomic bonds in the usual way. It is temporarily changing its internal phase under stress, then reversing that change. That is why these alloys became so valuable in devices that must flex, recover, and work inside tight spaces where ordinary metals would either stay bent or break. But the most important word here is trained. The material does not know every possible shape. It is processed, heat-treated, shaped, and engineered so that one form becomes its preferred high-temperature or unloaded state. The memory is a manufactured relationship between composition, structure, and transformation temperature. Change the amount of nickel, titanium, copper, or other elements. Change the heat treatment. Change the cold working. Change the microstructure, and the alloy's response can shift. A small change in composition can alter the temperature at which the material transforms. That is why making reliable shape memory devices is not as simple as buying a magical wire. It requires precision. The alloy must transform at the right temperature, with the right force, over the right number of cycles, without cracking, corroding, or losing its useful response too quickly. This is where the science becomes more mature and more interesting than the viral demonstration. You may see a bent wire straighten in hot water and think the entire subject is a trick about returning to shape. But engineers see a deeper question. Can motion be built into the material itself? In a normal machine, movement comes from motors, gears, hydraulics, pistons, hinges, or electronics. In a shape memory alloy, movement can come from the material changing phase. A thin wire can contract when heated and act like a small artificial muscle. A spring can open or close a valve when the surrounding temperature crosses a threshold. A small component can respond automatically without needing a complex motor or sensor, because the material itself is the sensor and the actuator at once. This is why shape memory alloys are studied for robotics, aerospace mechanisms, medical tools, adaptive structures, vibration control, and tiny devices where conventional machinery becomes too bulky. They offer a way to make matter active without making it complicated, but they also bring limits that honest science cannot ignore. Heating and cooling take time, so shape memory actuators are often slower than electric motors. Repeated cycling can cause fatigue, and fatigue is one of the great enemies of long-term reliability. The material can lose performance if pushed beyond its designed strain range. Its transformation does not happen at one perfectly sharp temperature, but often across a range, with hysteresis, meaning the heating path and cooling path do not match exactly. That gap can be useful in some designs and frustrating in others. The alloy can generate strong forces, but it can also be difficult to control precisely. It can recover shape but not from unlimited damage. It can seem almost alive, but it remains a physical system with boundaries. Those boundaries matter because they protect the wonder from becoming a lie. Shape memory alloys are not self-healing metals in the general sense. They do not repair cracks automatically just because they remember a form. They do not reverse every dent, every cut, every fatigue failure, or every broken bond. What they remember is not damage-free history, but a trained structural state reachable through a reversible phase transformation. And when you understand that difference, the phenomenon becomes even more beautiful. It is not fantasy. It is architecture responding to temperature and stress. It is the idea that a material can be given a hidden instruction. When the world warms, return. When the load disappears, recover. When the environment changes, move. In this way, material memory becomes less like nostalgia and more like a built-in rule. The alloy is not thinking backward. It is following an internal path that was prepared for it. And this changes how you see every object around you. Most materials appear passive because they wait for outside forces to shape them. A stone does not decide to roll. A beam does not decide to bend. A wire does not decide to close a circuit. But smart materials blur that boundary. They do not have minds, yet they respond. They do not have intention, yet they behave as if they were designed to answer a question. Shape memory alloys are among the clearest examples of this shift because they turn temperature and stress into motion. You begin to realize that the future of materials may not only be about making things stronger, lighter, or cheaper. It may be about making matter more responsive, more adaptive, more able to participate in the behavior of a machine or a body. A bridge could use materials that damp motion. A spacecraft could use components that unfold with heat. A small medical device could change shape after entering a narrow space. A robot could move through wires that contract like quiet metallic tendons. These are not dreams detached from reality. They are directions researchers and engineers continue to explore, always constrained by cost, fatigue, control, safety, and manufacturing difficulty. The emotional weight of the subject is subtle but powerful. The metal's memory is not a past it longs for, but a possibility encoded into its present. It reminds you that form is not always fixed. Sometimes form is temporary, waiting for the conditions that reveal what the material was prepared to become. A shape memory alloy, warmed at the right moment, does not perform a miracle. It performs a return. And in that return, you glimpse a larger truth about matter itself. Even the coldest, hardest-looking objects may contain hidden transitions, quiet thresholds, and stored behaviors that only appear when the world touches them in exactly the right way. Aerogels and almost weightless solids. Hold a piece of aerogel in your hand, and your brain struggles to accept that something can be solid while feeling almost like captured air. It may look like a pale blue ghost, a frozen cloud, a fragment of smoke that somehow learned to keep its shape. But aerogel is not smoke, not foam in the ordinary sense, and not a magic material floating outside the rules of physics. It is a real solid with an almost unbelievable internal structure, a delicate network of material threaded through a vast amount of empty space. In many silica aerogels, most of the volume is air, while the actual solid framework makes up only a tiny fraction of the object. That is why a block of aerogel can be so light that it feels unreal, as if your fingers are holding the outline of a solid rather than the solid itself. But the most important part is not simply that aerogel is light. The deeper wonder is how it is made. It begins as a gel, a wet material where a solid network and liquid are interwoven. If you simply dried that gel the normal way, the liquid would evaporate, surface tension would pull the tiny structure inward, and the network would collapse like a soaked sponge shrinking into itself. To create aerogel, scientists remove the liquid while preserving the fragile inner skeleton, often using special drying methods that prevent the pores from crushing. What remains is a solid that is mostly empty space, but not empty in a useless way. It is emptiness organized. It is air held inside a nanoscale labyrinth. And because heat travels poorly through that kind of structure, aerogels can be extraordinary insulators. Heat can move through solids, gases, and radiation. But in an aerogel, the solid path is thin and broken. The gas inside tiny pores cannot circulate freely like air in an open room, and the whole structure slows the transfer of energy. This is why aerogel can protect against extreme temperature differences, even when the material itself is almost weightless. You may have seen demonstrations where a flower or a piece of chocolate is shielded from intense heat by aerogel. And while those demonstrations can be dramatic, the real science behind them is not a trick. The material is forcing heat to take a difficult route. It is not blocking heat forever, and it is not indestructible. But it can slow heat flow so effectively that a very thin layer can perform like a much thicker ordinary insulator. That property made aerogels valuable for spacecraft, Mars missions, cryogenic systems, industrial insulation, and scientific instruments. NASA has used aerogel as thermal insulation on Mars missions, and also used aerogel in the Stardust mission to capture high-speed comet particles without destroying them completely. That use is especially beautiful because it shows another side of aerogel. It can be soft and open enough to slow tiny dust grains traveling at enormous speeds, leaving tracks inside the material like messages written by space itself. Imagine a particle from a comet, older than human civilization, entering a block of aerogel and being gradually slowed by a ghostly solid so light it seems barely there. The material becomes not just insulation but a net for cosmic history. And yet, to keep this honest, aerogel is not a universal miracle. Traditional silica aerogels can be brittle and dusty. They can crack, crumble, absorb moisture if not treated, and require careful handling. Their impressive properties depend on composition, density, pore size, manufacturing method, and whether they are reinforced or made into flexible blankets or composites. A perfect-looking block of aerogel in a photograph may be more fragile than it appears. Some modern aerogel products are made tougher by combining the aerogel with fibers or polymers, turning the fragile network into blankets, panels, or composites that can survive real use. But even then, aerogels are not stronger than everything. Not weightless, not invisible, and not automatically cheap or easy to produce at any scale. Their power comes from a trade-off. By making a solid incredibly porous, you gain low density and insulation, but you often lose mechanical toughness unless the structure is reinforced. That is the kind of truth materials science constantly teaches. Every material is a negotiation. Aerogel negotiates with matter by asking, how little solid can still count as a solid? How much emptiness can be held before structure disappears? How can air, usually a sign of absence, become part of a material's strength and function? This is why aerogel feels almost philosophical without needing exaggeration. A stone is solid because it is dense and continuous. A metal beam is solid because it carries load through a thick, connected body. Aerogel is solid in a different way. It is a skeleton so fine that most of what you hold is not the skeleton but the space inside it. And that challenges your instinct. You were taught to trust weight as proof of substance. Heavy things feel real. Dense things feel serious. But aerogel shows that reality does not always announce itself through heaviness. Sometimes the most advanced material in the room is the one that seems least present. Its strength is not brute force. Its secret is architecture. A network of tiny strands can create a macroscopic object. Pores too small to see can reshape how heat travels. A pale, fragile block can survive conditions that would overwhelm ordinary materials if used in the right way. And once you understand that, ordinary objects begin to look different. A wall is not just a wall. It is a structure deciding how heat, sound, moisture, and force pass through it. A jacket is not just fabric. It is trapped air, fibers, and barriers arranged to slow energy loss from your body. A spacecraft is not just metal. It is layers of materials each chosen to negotiate with radiation, vacuum, cold, heat, and impact. Aerogel belongs to this larger story of design through structure. It teaches that material performance can come not only from what atoms are present, but from how matter and emptiness are arranged together. That may be the most haunting lesson hidden in its lightness. Aerogel is almost weightless, not because it escapes mass, but because it uses so little solid matter so effectively. It is a reminder that emptiness can be engineered, that absence can become function, and that a material does not have to feel powerful in your hand to be powerful in the world. So when you see aerogel resting on someone's palm like a piece of blue mist, do not think of it as a novelty. Think of it as a question made solid. How much of a thing can be missing before the thing stops being real? Aerogel answers quietly. More than you think, far more than school ever prepared you for. Because here is a solid made mostly of void, and yet it can insulate, protect, capture, support, and survive in places where ordinary materials would fail. It is not nothing. It is not air pretending to be matter. It is matter stretched into a whisper, a solid skeleton holding space so carefully that emptiness itself becomes useful. Quantum dots and artificial atoms. A quantum dot is so small that it can make color depend not on pigment, dye, or paint, but on the size of a crystal only a few nanometers wide. That sentence sounds almost too delicate to matter. Yet, it is one of the reasons quantum dots have become some of the most important nanoscale materials in modern science. In the everyday world, color often feels like a surface property. A red object looks red because of the way its molecules absorb and reflect light. A blue dye looks blue because of its chemistry. A glowing neon sign has its own atomic emissions. But quantum dots add a stranger possibility. Take the same basic semiconductor material, make the particles smaller or larger, and the color of light they absorb or emit can shift. The material has not changed into a new element. The tiny crystal has changed size, and at that scale, size becomes a rule of energy. This happens because electrons and their missing partners, often called holes, are confined inside an extremely small region. In a large chunk of semiconductor, charge carriers can move through a broad landscape of energy. But in a quantum dot, the space is so limited that the allowed energy states become more separated, more discrete, more atom-like. That is why quantum dots are often called artificial atoms. They are not real atoms, because they do not have one nucleus surrounded by naturally bound electrons in the same way carbon, oxygen, or gold atoms do. They are made from many atoms arranged into a tiny semiconductor crystal or engineered structure, but the electrons inside them can be confined so strongly that they occupy distinct energy levels, somewhat like electrons in an atom occupy allowed states rather than every possible value. The phrase artificial atom is not meant to exaggerate. It is a useful comparison. A real atom's behavior is determined by its nucleus and electron structure. A quantum dot's behavior can be tuned by its size, shape, composition, surface chemistry, and environment. In that sense, it is an atom-like system that humans can design. And that design control is the doorway to its power. Make a quantum dot slightly smaller, and the energy gap often becomes larger. So it tends to emit bluer light. Make it larger, and the emitted light shifts toward redder colors. This is why quantum dots became important in display technology. They can produce very pure, narrow colors, helping screens create bright reds and greens with high efficiency and wide color range. When you hear about quantum dot televisions, the science behind the marketing is this. Tiny semiconductor particles help convert light into carefully selected colors. They are not portals, not tiny stars, not living crystals, but nanoscale light sculptors. Their color is controlled by quantum confinement, and the precision of that color is what makes them valuable. The 2023 Nobel Prize in Chemistry recognized Mungi Bawendi, Louis Bruce, and Alexei Ekimov for the discovery and development of quantum dots, and the Nobel Committee emphasized that these tiny particles have different colors depending on their size. and are now used in technologies such as television screens and LED lamps. But their story goes beyond displays. Because quantum dots interact with light so strongly and tunably, they have been studied for biological imaging, solar cells, photodetectors, LEDs, lasers, sensors, and quantum information technologies. In medicine and biology, quantum dots can act as bright fluorescent labels, helping researchers track cells, proteins, or processes under microscopes, though safety and toxicity must be handled carefully, especially for dots containing heavy metals such as cadmium. In energy research, they are explored because their light absorption and electronic behavior can be tuned by design, though turning laboratory promise into durable, cheap, scalable devices is never simple. In quantum information, single quantum dots can sometimes hold or emit individual photons, or confine single charges and spins, making them interesting for devices that may one day help with quantum communication or computing. But here again, the truth must stay clear. Quantum dots are not already solving every technological problem, and not every dot is useful for every purpose. A dot that is excellent for a screen may not be safe for medicine. A dot that is promising for quantum information may require extreme control, very low temperatures, precise fabrication, or complex optical systems. A dot that shines beautifully in a lab may degrade, blink, lose efficiency, or become difficult to manufacture consistently. Their surfaces matter enormously because at nanometer size, a large fraction of the atoms sit near the outside. A small defect, dangling bond, impurity, or poor coating can change how the dot glows or how stable it remains. That is why quantum dot chemistry is not just about making tiny crystals, but about controlling their surfaces, shells, ligands, and surrounding environment. Many high-quality quantum dots use a core shell structure where one semiconductor forms the center and another material coats it, protecting it and improving emission. This is almost like giving the artificial atom a carefully designed skin, not for beauty, but for stability and performance. The smaller matter becomes, the more the boundary matters. In a large object, most atoms are buried inside. In a quantum dot, the surface can dominate the personality of the whole particle. That is one of the most important lessons here. The nanoscale is not just a smaller version of the world you know. It is a different regime where size, surface, and quantum behavior become inseparable. A gold ring and a gold nanoparticle do not necessarily behave the same. A chunk of semiconductor and a quantum dot made from related material do not interact with light in the same way. You cannot simply shrink something and expect the same rules to remain visible. Sometimes shrinking does not make matter weaker or less important. It makes hidden behavior louder. Quantum dots prove this in one of the most beautiful ways possible, by turning size into color. And perhaps that is why they feel so fascinating. They take one of the oldest human experiences, seeing color, and connect it to one of the smallest engineered structures we can make. A child sees red, green, and blue as simple sensations. A scientist looking at quantum dots sees confinement, energy gaps, electron hole pairs, surface chemistry, and nanoscale design. Both are looking at light, but one sees the feeling, and the other sees the machinery. The wonder is that both are real. Quantum dots sit between those worlds. They are small enough to obey rules that do not fit ordinary intuition, but useful enough to appear in everyday technology. They are artificial atoms not because they replace nature's atoms, but because they give humans a way to build atom-like behavior from matter arranged at a larger scale. That idea changes what a material can be. In the past, you might choose a material for its natural color, hardness, melting point, or conductivity. With quantum dots, you begin designing properties by choosing size and structure. You do not only ask, what is this substance? You ask, how small is it? How is it confined? How is its surface protected? What color will it speak when excited by light? And in that question, matter becomes more like an instrument than a passive object. A violin's note changes with string length, tension, and shape. A quantum dot's light changes with size, composition, and confinement. The note is not arbitrary. It is built into the structure. This is why quantum dots matter so much. They show that the nanoscale is not just a place of tiny things, but a place where properties become tunable. They remind you that the universe does not only make atoms. It allows us to build structures that behave atom-like in selected ways. It allows us to create crystals whose color is measured not by paint, but by diameter. It allows us to design artificial systems where electrons feel trapped in a tiny room and respond with discrete, luminous answers. And maybe the deepest lesson is this: matter is not finished when you know its chemical name. A material can carry different possibilities depending on its size, surface, and confinement. A tiny dot of semiconductor can glow like a carefully tuned lamp, tag a cell in a microscope, convert light in a device, or act as a building block for future quantum technologies. It is not magic. It is not science fiction pretending to be real. It is the real strangeness of matter at a scale where the rules of the large world begin to loosen, and a crystal too small to see with your eyes can hold a color bright enough to change the screens you look at every day. Crystals that change when you shine light on them. Some crystals do not merely sit under light, they answer it, changing color, bending, twisting, cracking, or even jumping as if a silent signal has passed through their structure. This sounds like the beginning of a fantasy story, but it belongs to a real field of materials science where certain crystals are designed so that light can trigger molecular change. To understand why this is so strange, begin with the way you normally imagine a crystal. A crystal feels fixed. It suggests hardness, order, silence, and stillness. Salt crystals, quartz, diamond, sugar grains, snowflakes, they all carry the feeling of atoms or molecules locked into place, arranged with discipline, repeating their pattern over and over. A crystal does not seem like something that should move when a beam of light touches it. It seems like something that should either reflect light, absorb it, or perhaps warm up slightly. But some crystals contain molecules that are light sensitive, and when these molecules absorb particular wavelengths, they can change shape, switch between two forms, or enter a new chemical arrangement. In a liquid, such molecular changes might happen quietly, hidden inside random motion. But in a crystal, the molecules are packed in an ordered way, like people seated shoulder to shoulder in a theater. If one molecule tries to change shape, it cannot do so freely. It pushes against its neighbors. Those neighbors push back. The tiny change becomes strain. And if enough molecules respond in a coordinated region of the crystal, the whole object can bend or move. That is the key. The light does not grab the crystal like a hand. It changes the molecules inside, and the crystal's own order converts that microscopic change into visible motion. One common kind of light-responsive molecule is azobenzene, which can switch between a longer, straighter form and a bent form when exposed to certain light. Another important family is diarylethene, known for photochromism, meaning it can change color when light drives it between different molecular forms. These names may sound technical, but the idea is simple enough to feel. A molecule is not always a rigid statue. Some molecules are more like tiny hinges, switches, or folding tools. Light can supply the energy that flips the hinge. In a crystal made from many such molecules, 1,000,000 tiny switches can become one larger response. Sometimes the result is a color change, because the new molecular form absorbs light differently. A crystal that was pale may become blue, purple, yellow, or red under ultraviolet light, then return under visible light or with time, depending on the chemistry. This is not paint appearing on the surface. It is the internal electronic structure of the molecules changing how they interact with light. The color is a message from the molecular arrangement. In other cases, the result is motion. A thin crystal may curve away from the light source because the illuminated side changes faster than the shaded side. One face of the crystal expands, contracts, or reorganizes slightly, while the other side lags behind, and that difference makes the crystal bend. It is the same broad reason a bimetal strip bends when heated, except here the trigger is not simply heat spreading through two metals. It is light causing molecular transformation inside an ordered organic crystal. Some crystals move gradually, like tiny arms curling under a lamp. Others react suddenly through a photosalient effect, where built-up strain releases so quickly that the crystal jumps, splits, or snaps from one place to another. The crystal does not become alive, but it can look alive because the motion appears purposeful. It is not purposeful. It is stored stress escaping through structure, and that distinction matters. Light-responsive crystals are not magic stones with willpower, not conscious materials, and not simple solar-powered machines ready to replace engines. They are small, delicate systems where chemistry, crystal packing, light penetration, elasticity, and heat all compete. Their behavior depends on wavelength, intensity, crystal thickness, molecular alignment, defects, humidity, temperature, and how many times the crystal has already switched. A crystal may work beautifully under a microscope, but fail when scaled up. It may bend in one direction only because its molecular packing is uneven. It may fatigue after repeated cycles. It may crack because crystals are often rigid and fragile. It may respond only to ultraviolet light, which is not always convenient or safe for practical devices. But these limits do not weaken the wonder. They make the wonder sharper. The real achievement is not that scientists have made a universal light-powered robot from crystal. The real achievement is that a solid, ordered material can directly convert absorbed light into mechanical work. No wires, no battery, no moving gears, just photons entering a molecular lattice and producing shape change. This is why researchers study photomechanical crystals as possible building blocks for tiny actuators, optical switches, soft robotic components, sensors, and adaptive materials. An actuator is simply something that creates movement. And these crystals suggest a future where movement might be triggered remotely by light, with no direct contact. Imagine a microscopic valve that opens when illuminated, a tiny gripper that bends under a laser, a surface that changes its texture when exposed to a certain color, or a material that stores information in two different light-controlled states. Some of these ideas are still experimental, and some may never become practical in the simple form we imagine. But the direction is real. Light can be more than illumination. It can be a command. It can be an energy source. It can be a switch. And in the right crystal, that command can become motion. The deeper lesson is about order. If the same light-sensitive molecules were randomly scattered in a soft material, their individual changes might cancel out or become messy. But a crystal lines them up. It gives their tiny movements a shared geometry. This is why crystals are so powerful in this field. Their rigidity, which seems like a weakness, can become part of the mechanism. Because the molecules cannot easily move freely, their frustration becomes force. The crystal holds them in formation, and light disturbs that formation in a controlled way. You could almost say the crystal turns molecular discomfort into movement. That phrase is poetic, but the physics behind it is real. Internal strain builds, the lattice responds, and the visible object changes shape. This also reveals something easy to miss about light itself. We usually treat light as something that lets us see objects, not something that objects can obey. You shine a flashlight on a wall, and the wall appears. You shine sunlight on a leaf and photosynthesis begins. You shine ultraviolet light on certain molecules, and bonds can rearrange. Light is not only a messenger, it carries energy, and matter can be designed to receive that energy in specific ways. In photoresponsive crystals, that energy does not merely become heat. It can become a new molecular state, a change in color, or a mechanical movement. The crystal becomes a translator between light and form. And when you understand that, the quiet objects around you start to feel less passive. A material is not just what it looks like in darkness. It is also what it is capable of becoming under the right stimulus. Shine the right light, and a crystal may reveal a hidden second personality. Not because it was false before, but because matter often contains multiple allowed states, and the environment decides which one becomes visible. That is the honest beauty of these crystals. They are not supernatural. They are conditional. They respond only when the wavelength fits, when the molecules are arranged correctly, when the structure is thin enough or flexible enough, when the transformation can happen without destroying the crystal. Their motion is small, sometimes microscopic, sometimes fragile, often difficult to repeat perfectly. But within those limits, they show something extraordinary. A solid can be instructed by light. A crystal can act as a tiny machine without having machine parts. A beam can change not only what you see, but what the material does. And perhaps this is why crystals that change under light feel so captivating. They take the oldest symbol of stillness, a crystal, and reveal that stillness is not always silence. Sometimes it is readiness. Sometimes the order inside matter is waiting for one precise color of light to loosen a hidden hinge, release a stored strain, or open a molecular door. The crystal was never alive, but it was never merely dead either. It was a structure with possibilities folded inside it, and light was the key that showed you one of them. Smart glass and light-controlled transparency. A window can seem like the most passive object in a building, just a silent sheet between inside and outside, until you realize that glass can be taught to decide how much of the world it lets through. Smart glass is the name we give to glazing that can change its transparency, tint or light transmission in response to electricity, heat, or light itself. And the most important thing to understand is that it is not one single invention, but a family of materials that make windows active instead of fixed. Ordinary glass has one personality. It may be clear, tinted, coated, reflective, or insulated, but once installed, it mostly behaves the same way every hour of the day. Smart glass changes that. In one moment, it can allow daylight to enter a room. In another, it can darken to reduce glare, block some solar heat, protect privacy, or help lower the load on heating and cooling systems. Electrochromic smart windows, one of the best-known types, work by using a small electrical voltage to move ions and electrons into or out of thin material layers, often involving tungsten oxide or related compounds. And that movement changes the way the window absorbs and transmits light. In simple terms, the glass is not being painted darker from the outside. Its internal optical state is being changed by controlled chemistry. Some electrochromic devices contain several layers: transparent conductors, ion storage layers, an electrolyte, and an electrochromic layer. When voltage is applied, tiny charge particles shift position, and the glass gradually changes from clearer to darker or back again. This process is usually not instant like flipping a light switch. Large panels may take minutes to fully tint or clear because ions physically move through materials. But that slower pace is also part of its nature. Smart glass is less like a screen flashing an image and more like a window breathing into a different state. Other technologies work differently. Suspended particle devices use microscopic particles in a film that align under electricity to let more light through, then scatter or absorb light when the power state changes. Polymer dispersed liquid crystal glass can turn from frosted to transparent when an electric field aligns liquid crystal droplets, often used for privacy partitions. It is very good at switching between private and clear, though it does not necessarily block heat in the same way as some solar control glazing. Thermochromic glass changes because of temperature, darkening or shifting transmission when heat rises, without needing active wiring in some designs. Photochromic glass changes under certain light, familiar from eyeglass lenses that darken in sunlight, though architectural versions have their own challenges. So when people say smart glass, you should ask, smart in what way? Does it respond to electricity, sunlight, heat, or a control system? Does it block visible glare, infrared heat, ultraviolet radiation, or mainly create privacy? Does it need power only to switch, or power to stay in one state? Does it tint uniformly, switch quickly, last for many cycles, and remain affordable enough for a real building? The honest answer depends on the technology. This is why smart glass is not a magic wall that turns invisible on command, nor a perfect energy-saving solution for every climate. A building in a hot, sunny region may benefit from reducing solar heat gain during peak hours. A cold region may sometimes want more solar warmth, not less. A room with screens may care about glare. A hospital may care about privacy and daylight. An office tower with a huge glass facade may care about cooling load and occupant comfort. Smart windows are useful because they can adapt, and adaptation is often more valuable than a single fixed setting. A 2023 review in the Innovation Materials describes thermochromic and electrochromic smart windows as technologies designed to regulate light and heat dynamically for building energy applications. And electrochromic windows are especially studied because they can adjust solar radiation transmission instead of simply accepting whatever sunlight arrives. The US Department of Energy has also discussed electrochromic windows as a way to improve the thermal and optical performance of large glass facades, potentially reducing glare and helping with building energy performance when designed correctly. But the deeper story is not only about saving electricity, it is about changing the role of a surface. A traditional wall separates, a traditional window connects. Smart glass does both, but with a variable boundary. It can make a room feel open in the morning, calmer at noon, private in the evening, and protected during harsh sun, all without curtains moving or blinds rattling. It turns transparency into a controllable property, and that is a strange idea if you sit with it. Transparency feels like honesty. A clear window seems to say, nothing is hidden. A dark window seems to say, something is withheld. But in smart glass, transparency becomes a state, a choice, a material response. The window is no longer simply clear or not clear. It becomes conditional. It becomes part of the building's nervous system, responding to sensors, timers, switches, sunlight, temperature, or human preference. In the best designs, this can improve comfort because people want daylight but not eye strain, view but not overheating, openness but not exposure. Smart glass tries to balance those contradictions through material change rather than mechanical covering. And yet, this balance is difficult. Electrochromic windows can be expensive. Some have limited color neutrality, meaning they may tint blue, gray, or bronze rather than staying perfectly natural. Switching speed can vary. Long-term durability matters because windows must survive years of sunlight, heat, cold, moisture, cleaning, and electrical cycling. Manufacturing large uniform panes is harder than making tiny laboratory samples. Some systems require careful installation and control electronics. Some privacy glass becomes hazy rather than truly dark. And while that is useful for blocking views, it may not reduce solar heat enough. Some thermochromic windows respond automatically, which sounds elegant, but automatic response can also be a limitation if the occupant wants control. These are not flaws that destroy the concept. They are the real engineering questions that decide where smart glass makes sense. The fascinating part is that each limitation points to a deeper truth. Windows are not simple holes filled with glass. They are energy devices. They shape how heat enters, how light spreads, how people feel, how much artificial lighting is needed, how much air conditioning runs, and how connected a room feels to the outside world. In cities full of glass towers, a window is not just architecture, it is part of the climate behavior of the building. That is why researchers are exploring more advanced versions, including dual-band and multi-band electrochromic windows that try to control visible light and near-infrared heat separately, so a room might keep a clear view while reducing invisible heat, or allow warmth while limiting glare depending on the season. Reviews describe dual-band smart windows as promising because visible and near-infrared transmission can be regulated more independently, which could improve lighting and thermal efficiency compared with simpler tinting approaches. Some newer research even explores smart windows that combine tint control with energy harvesting or storage, though many such ideas remain under development and must prove cost, lifespan, safety, and scalability before becoming common. So the real wonder of smart glass is not that it makes buildings look futuristic. It is that it turns an ancient material into an active interface. Humans have used glass for centuries to let light in while keeping weather out. Now we are asking glass to do something more subtle, to negotiate with the sun. Let in enough light to keep a room alive, block enough heat to keep it comfortable, reveal enough of the outside world to preserve connection, hide enough to protect privacy, and shift all of this without needing the user to constantly fight the environment with blinds, curtains, lamps, and air conditioning. That is a profound change in what a material can be. Glass used to be a fixed compromise. Smart glass is an adjustable compromise. It does not eliminate the outside world. It tunes the relationship with it. And maybe that is why this technology feels quietly philosophical. A window is a boundary you can see through. It is both separation and invitation. When that boundary becomes responsive, the building begins to feel less like a sealed box and more like a living skin. Not alive in the biological sense, but sensitive in the material sense. It can darken under command, clear when openness is wanted, soften glare, preserve a view, and change the mood of a room without moving a single curtain. Smart glass reminds you that transparency is not always a fixed condition. Sometimes it is a decision written into matter, a controlled exchange between light, heat, privacy, and comfort. And as cities grow hotter, buildings become more energy hungry, and humans spend more of life indoors, the humble window may become one of the most important places where material science meets daily experience. Not because glass suddenly becomes magical, but because it becomes thoughtful, a surface that no longer only lets the world in, but asks how much of the world should enter, when, and why. Self-healing materials. A crack is usually the beginning of the end, but in self-healing materials, damage can become the signal that starts the repair. This is the quiet revolution behind self-healing materials. Not objects that magically restore themselves after any disaster, not walls that rebuild from rubble, not phone screens that erase every shatter like time running backward, but materials designed so that small damage can trigger a built-in response. In ordinary materials, a crack is dangerous because it concentrates stress. A tiny flaw in a coating, a bridge component, a polymer panel, or a piece of concrete can grow slowly under heat, moisture, vibration, pressure, or repeated use. At first, the damage may be almost invisible. Then it spreads. Then the material loses strength, lets water in, corrodes, leaks, fails, or breaks. Most of engineering is built around preventing that story from happening too soon. Make the material thicker, inspect it often, replace it before failure, seal it from the environment, or accept that every object has a limited life. Self-healing materials ask a different question. What if the material could respond to early damage before humans even notice it? The simplest way to imagine this is a polymer filled with tiny capsules of healing liquid. When a crack forms, it breaks some of these capsules, releasing the liquid into the damaged area. If the right catalyst or chemical trigger is present, the liquid hardens and bonds the crack faces together, partially restoring the material. This is called an extrinsic self-healing system because the healing agent is stored inside the material like a hidden supply. It is not alive. It is more like a wound dressing embedded before the wound exists. The crack opens the capsule releases the repair chemistry, and the material seals some of its own damage. But there is a limit. Once those capsules are used, that local supply is gone. The same area may not heal repeatedly unless the design includes a more advanced network. That is why researchers also explore vascular self-healing materials, where tiny channels run through the material like artificial blood vessels, carrying repair agents that can flow toward damaged regions. This idea is inspired by biology, but it is not biology copied perfectly. Your skin heals because living cells sense damage, communicate, divide, rebuild tissue, fight infection, and remodel the area over time. A self-healing polymer or composite has no cells, no immune system, no metabolism. It must rely on chemistry, structure, diffusion, swelling, heat, moisture, pressure, or light. Still, the inspiration is powerful. Nature rarely builds materials that simply wait to fail. Bone can remodel, skin can close wounds, trees can seal damage, shells can grow new layers. Engineering materials have traditionally been more silent, more passive. Self-healing research tries to give them a small piece of that responsiveness, not by making them alive, but by giving them a mechanism to react when damaged. There is another kind of self-healing called intrinsic healing, and it works differently. Instead of storing separate repair fluid in capsules, the material itself is built with bonds or interactions that can break and reform. Some polymers contain reversible chemical bonds, hydrogen bonding, ionic interactions, metal ligand connections, or dynamic networks that can reconnect when the damaged surfaces are brought together, sometimes helped by heat, light, pressure, moisture, or time. In these materials, healing is not a one-time patch released from a broken container. It can sometimes happen repeatedly because the repairability is part of the molecular structure. But intrinsic systems have their own challenges. A material that heals easily may be too soft or weak. A material that is very strong may not allow enough molecular movement for the broken surfaces to reconnect. This is one of the central trade-offs in the field. Healing requires mobility, but strength often requires rigidity. A soft gel can rejoin more easily than a hard structural plastic. A tough aerospace composite may resist damage, but once cracked, it may be difficult to make it heal deeply without weakening its original performance. So self-healing materials are always a negotiation between strength, speed, durability, cost, repeatability, and the kind of damage being repaired. A tiny scratch in a coating is not the same as a deep crack in a load-bearing beam. A surface scuff may heal through polymer flow or reversible bonding, while a structural fracture may require a much more serious mechanism. Concrete offers another fascinating example. Concrete is strong in compression, but it cracks, and those cracks can let water and salts enter, leading to corrosion of steel reinforcement and long-term deterioration. Self-healing concrete can use several approaches. Some rely on unhydrated cement particles that continue reacting when water enters small cracks. Others use capsules containing repair agents. One of the most intriguing approaches uses bacteria or microbial spores embedded in the concrete along with nutrients. When water enters a crack, dormant bacteria can become active and help precipitate calcium carbonate, a mineral similar to limestone, sealing the crack from within. This does not mean the concrete becomes alive like skin, and it does not mean a collapsed building can grow back. The cracks must be small enough. The bacteria must survive the harsh alkaline environment. Moisture must be present. Nutrients must be available, and the healing products must form in the right place. Still, the idea is powerful because it turns water, the very thing that often worsens concrete damage, into part of the repair trigger. The crack opens. Water enters. The hidden system activates. Mineral forms. The pathway narrows or closes. It is not perfect, but it is a shift in philosophy. Instead of treating every crack as a silent failure, the material treats some cracks as a message. Self-healing coatings follow the same logic in a different setting. A protective coating on metal is meant to keep moisture, oxygen, and corrosive chemicals away from the surface. If the coating is scratched, corrosion can begin exactly where the protection has failed. A self-healing coating may contain microcapsules, corrosion inhibitors, or responsive chemistry that releases protective agents when damage occurs or when corrosion starts changing the local environment. The goal is not to make the metal immortal, but to slow the chain reaction between scratch, exposure, corrosion, and failure. That is where many self-healing materials may first matter most. Not in dramatic sci-fi repairs, but in small, early interventions that extend service life. A bridge that lasts longer before major repair, a coating that seals microcracks, a composite that recovers some strength after impact, a flexible electronic material that reconnects after being stretched or cut, a soft robot skin that repairs minor damage, a battery component that resists cracking, or a medical material that survives repeated deformation. These are the more realistic directions. And the reason this matters is bigger than convenience. Materials fail everywhere around us. They fail in roads, aircraft, buildings, pipelines, electronics, medical devices, wind turbines, ships, vehicles, and infrastructure we barely notice until it breaks. Every failure costs energy, money, resources, and sometimes lives. If materials can heal small damage early, they may last longer, need fewer replacements, reduce maintenance, and make structures safer. But honesty is essential here. Self-healing materials are not a single technology ready to transform every industry overnight. Many work only in laboratory conditions. Some need heat that is too high for practical use. Some heal slowly. Some recover only part of their original strength. Some require damaged surfaces to touch closely. Some cannot heal repeated damage in the same place. Some are too expensive. Some healing agents may leak, age, evaporate, react too soon, or weaken the base material. In concrete, microbial systems must survive years inside a hostile environment. In polymers, dynamic bonds may improve healing, but reduce mechanical stiffness or temperature resistance. In composites, adding capsules or channels can interrupt the material's original structure. Every self-healing design brings a cost, because the material must carry both its normal job and its repair system. That is the deep engineering challenge. You cannot simply add healing and expect everything else to remain unchanged. A material that can heal must be designed as a whole system, where damage detection, transport, reaction, bonding, and long-term stability all work together. And this is what makes the subject so fascinating. Self-healing materials change the meaning of damage. In a normal object, damage is only loss. In a self-healing object, damage can also be information. It tells the material where repair is needed. It breaks the capsule, opens the channel, exposes the reactive surface, lets water in, changes the local chemistry, or brings molecular bonds close enough to reconnect. The wound becomes the instruction. There is something quietly profound in that, but it does not require pretending matter has feelings. The beauty is not that the material wants to heal. The beauty is that humans have learned to design matter so that failure can trigger function. We are beginning to build materials that are not merely strong at the beginning of their life, but responsive during their life. That is a different kind of intelligence, not mental intelligence, but structural intelligence. A self-healing material does not think, but it is arranged so that its response is already waiting inside it. Degenerate matter in white dwarfs. A white dwarf is a star that has stopped burning like a star, yet refuses to collapse because the smallest particles inside it are obeying a rule deeper than heat. When a star like the Sun reaches the end of its active life, it does not have enough mass to become a neutron star or black hole. Instead, after shedding its outer layers, it leaves behind a dense exposed core, a white dwarf. From far away, it may look like a faint stellar ember, a small object slowly cooling in the dark, but inside it is one of the strangest forms of matter in the universe. It is not held up by normal fire. It is not supported by the outward pressure of nuclear fusion the way a living star is. The fusion has mostly stopped. The furnace is gone. And yet the star does not simply fall inward into nothing. Something else pushes back, not a heat pressure in the ordinary sense, but a quantum pressure created by electrons packed so tightly that they resist being squeezed into the same states. This is called electron degeneracy pressure, and it comes from the Pauli exclusion principle. Electrons cannot all crowd into one identical condition, even if gravity desperately tries to force them there. In everyday matter, this rule is hidden under ordinary chemistry and structure. In a white dwarf, it becomes the main pillar holding up an entire star. NASA describes white dwarfs as being supported by electron degeneracy pressure, a quantum mechanical effect that resists gravitational collapse. The result is almost impossible to hold in your imagination. A star's worth of material compressed into something roughly Earth-sized, with density so extreme that a small spoonful of white dwarf matter would weigh tons on Earth. But the most important part is not the shocking density. It is the reason that density does not keep increasing forever. Heat can fade, light can leak away. A white dwarf can cool for billions of years. But electron degeneracy pressure does not depend on the star being hot in the same way ordinary gas pressure does. It comes from confinement, from the quantum rules that appear when electrons are forced into an incredibly crowded space. That is why a white dwarf can continue standing even as it cools, like an ember whose glow weakens while its internal quantum scaffolding remains. This is different from a normal star, where gravity presses inward and heat from fusion pushes outward. A main sequence star is a balance between burning and gravity. A white dwarf is a balance between gravity and quantum refusal. The word degenerate can sound negative, almost like decay or corruption, but in physics it has a specific meaning. Degenerate matter is matter packed so tightly that the quantum rules governing particles dominate its pressure and behavior. It is not morally degenerate, not disordered trash, not broken matter. In fact, it is matter organized by a rule so strict that gravity cannot ignore it. Think of a theater where every seat represents an allowed state. In an ordinary crowd, people wander freely, many spaces are open, and movement is easy. But in degenerate matter, the seats fill from the bottom upward, and electrons are forced into higher and higher states, because no two can occupy the same exact quantum seat. Squeezing the star further is like trying to force more people into a room where the seating rule cannot be violated. The resistance does not come from people pushing with muscles. It comes from the rule of the room itself. That is what makes white dwarf matter so strange. It is not stiff because it is cold metal. It is stiff because quantum identity has become pressure. But this support has a limit. If a white dwarf gains too much mass, often by pulling material from a companion star or merging with another white dwarf, gravity can overwhelm electron degeneracy pressure. This maximum stable mass is called the Chandrasekhar limit, named after Subrahmanyan Chandrasekhar, and it is about 1.4 times the mass of the Sun for typical white dwarf conditions. Above this limit, electron degeneracy pressure is no longer enough to support the star against collapse. The Chandrasekhar limit is widely described as the maximum mass of a stable white dwarf, supported primarily by electron degeneracy pressure. This does not mean every white dwarf explodes the moment it approaches that number in exactly the same way. Real astrophysics is more complex, involving composition, rotation, magnetic fields, accretion, and binary evolution. But the basic lesson is real. Quantum pressure can hold up a dead star, but not without limit. If the balance fails, the result can be catastrophic, sometimes leading to a type Ia supernova, one of the most important kinds of stellar explosions in astronomy. These explosions are not just violent endings. They have helped scientists measure cosmic distances because many type Ia supernovae have predictable brightness patterns. In a strange way, the hidden pressure inside dead stars helped humans map the expansion of the universe. A white dwarf's interior also changes how you think about temperature. It may be extremely hot by human standards, especially when young. Yet the pressure holding it up is not mainly ordinary heat pressure. This is one reason white dwarfs are so different from familiar hot objects. If you heat air in a balloon, the pressure rises because particles move faster. If the balloon cools, the pressure drops. But in a white dwarf, much of the support comes from the crowding of electrons, not merely their thermal agitation, so the star can shine less and less over cosmic time while still resisting collapse. It becomes like a cooling coal held together by a law older than atoms, a remnant whose brightness fades, but whose structure remains locked by quantum mechanics. There are also different kinds of white dwarfs. Many are made mostly of carbon and oxygen, the ashes left by stars that once fused helium in their cores. Some lower mass white dwarfs can be helium-rich, often shaped by binary star evolution. More massive ones may contain oxygen, neon, and magnesium. Their surfaces can be dominated by hydrogen or helium atmospheres, and astronomers classify them by the fingerprints in their light. But inside, the central idea remains. Ordinary atoms are crushed into a dense state where nuclei and electrons no longer behave like matter in your hand. The nuclei still exist, often arranged in a dense background, while the electrons form the degenerate sea that supplies the pressure. OpenStax's astronomy text emphasizes that in white dwarfs, it is the degeneracy pressure of electrons, not nuclei, that halts the collapse of the core. This detail matters because it keeps the story precise. A white dwarf is not a giant atom, not a neutron star, not a black hole waiting quietly in disguise. It is its own category of cosmic remnant, supported by electrons rather than neutrons, limited by the Chandrasekhar mass rather than event horizons, and doomed not to explode immediately in most cases, but to cool slowly over immense timescales. Eventually, over periods far longer than the current age of the universe, white dwarfs are expected to fade toward black dwarfs. cold dark remnants that have not yet had time to exist because the universe is still too young. So every white dwarf we see is still warm enough to glow, still carrying leftover heat from its formation, still writing the long afterword of a star's life. And perhaps that is the most haunting part. A white dwarf is not alive in the stellar sense, but it is not simple death either. It is what remains when fusion ends and gravity asks one final question. Can anything stop me now? The answer comes not from flames, not from chemical bonds, not from pressure like air in a tire, but from electrons refusing to be made identical. A rule from quantum physics becomes a wall strong enough to hold up a star. This should change the way you feel about matter, the chair beneath you, the air around you, the blood in your body. All of it seems ordinary because it exists under gentle conditions. But under the weight of a dead star, matter reveals a hidden legal system, a set of rules about identity, crowding, and possibility that only becomes visible when gravity becomes extreme. A white dwarf is a cosmic reminder that the universe is not held together only by big forces. Sometimes the fate of a star depends on the behavior of particles too small to see. Sometimes the smallest rules create the largest structures. And as a white dwarf cools in silence, it carries that truth into the dark. Even after the fire goes out, matter may still have one final way to resist being crushed into oblivion. Topological materials and protected edges. A topological material can hide its most important behavior not in its center, but along its edges, where electrons move as if the boundary itself has become a protected road. At first, this sounds strange because when you think about a material, you usually imagine its inside deciding everything. If a metal conducts electricity, you expect the whole piece to help carry current. If an insulator blocks current, you expect the whole piece to resist it. But topological materials break that simple expectation in a way that feels almost like a secret built into the shape of matter. A topological insulator, for example, can behave like an insulator in its bulk, meaning the interior does not let electrons move freely, while its surface or edge can conduct. The middle says no, but the boundary says yes. And this is not because the edge is dirty, damaged, or accidentally different. It is because the quantum structure of the material forces special states to appear at the boundary between two different kinds of order. The topological material on one side and ordinary space, or an ordinary material on the other. The word topology comes from a branch of mathematics that studies properties that remain unchanged even when a shape is stretched or bent without being torn. A coffee mug and a donut are often compared in topology because each has one hole, even though they look completely different. In topological materials, the comparison is not about mugs and donuts literally hiding inside crystals. It is about the idea that some properties are not easily changed by small distortions. A normal material property may depend heavily on local details. A defect here, an impurity there, a tiny crack, a rough edge. But a topological property is tied to a deeper global pattern in the material's quantum states. As long as the essential symmetry and energy gap remain intact, the boundary states can persist even when the edge is imperfect. This is what people mean by protected edges. It does not mean invincible edges. It does not mean electrons can pass through anything with zero loss forever. It means these conducting states are unusually robust against certain kinds of disorder that would normally scatter electrons backward and slow them down. In some two-dimensional topological insulators, the edge channels are described as helical. Electrons moving one way are tied to one spin orientation, while electrons moving the opposite way are tied to the opposite spin. Because of this connection, an electron cannot easily reverse direction unless something also changes its spin or breaks the protecting conditions. A small non-magnetic defect may be like a pebble on the road. The electron can go around it without being thrown backward in the ordinary way. This is why topological materials became so exciting for ideas about low-power electronics, spintronics, quantum devices, and protected signal transport. The dream is simple to say. If current can flow along special edges with less scattering, maybe future devices could carry information with less wasted energy. But the honest science is more careful. Real materials are never perfect. Edges can be messy. Samples can contain impurities. Temperatures matter. Magnetic disturbances can break time reversal protection in some systems. Electron interactions can create unexpected backscattering. Contacts between a device and measurement wires can introduce resistance. And even when the topological states exist, turning them into practical technology is extremely difficult. The protected edge is not a fantasy highway where nothing ever goes wrong. It is a quantum channel whose protection depends on the right conditions being preserved. That difference matters because the truth is already astonishing enough without exaggeration. The remarkable part is that the boundary of a material can carry information about the deeper identity of the whole material. You could inspect one small patch in the middle and think it looks ordinary, but the edges reveal that the material belongs to a different class. This is one of the strangest lessons of topology in physics. Sometimes the important feature is not visible in the local substance alone, but in how the entire quantum system is organized. It is like judging a book not by one word on one page, but by the hidden pattern connecting all its chapters. The edge becomes the place where that hidden pattern must speak. And topological behavior is not limited only to electrons in solids. Similar ideas now appear in photonics, where light is guided along protected paths, in mechanical systems, where vibrations can travel around edges, in acoustic systems, where sound can be directed in unusual ways, and in cold atom experiments, where scientists build artificial systems to study topological states under controlled conditions. Each platform has different physics, but the central idea echoes. A boundary can host motion that is protected by the structure of the system's deeper order. That should change how you imagine edges. In everyday life, an edge feels like a weakness. A crack begins at an edge. A surface gets scratched. A border is where things fray, rust, wear down, or break apart. But in topological materials, the edge can be the most alive part of the object, the place where motion is allowed precisely because the interior is locked. The boundary is not merely the end of the material. It is the consequence of what the material is. And that is a beautifully strange reversal. The outside becomes a message from the inside. The surface becomes proof of an invisible order. The edge becomes a road written by mathematics into matter. Still, this does not mean topological materials are easy to explain by ordinary intuition. They belong to a world where electrons are not tiny balls traveling through little pipes, but quantum waves moving through energy landscapes. The material's bands, gaps, symmetries, and spin behavior shape where motion is allowed. You do not need equations to feel the meaning. The interior is quiet because the electrons there have no easy allowed path, while the edge carries special states because the material's deeper topology demands that something connect one side of the gap to the other. It is less like a crack in a wall and more like a river appearing exactly where two landscapes meet. The river is not there by accident. It is required by the terrain, and perhaps that is why topological materials feel so profound. They show that matter can have hidden identity beyond chemistry, beyond strength, beyond color, beyond conductivity in the ordinary sense. Two materials may look similar, have similar ingredients, or appear equally solid, yet one may carry a topological order that gives its edges extraordinary behavior. This means the universe has categories of matter that are not obvious to touch or sight. They are discovered by how quantum states connect, how symmetries are respected, and how boundaries behave. In a way, topological materials remind you that the most important properties of a thing are not always in the center, where everyone looks first. Sometimes they are revealed at the margin. Sometimes the edge tells the truth. And when electrons move along that edge with unusual protection, they are not escaping physics. They are following a deeper version of it. A topological material does not promise a perfect future by itself, but it opens a door to one of the most elegant ideas in modern science. That structure can protect motion, that boundaries can carry hidden order, and that matter may contain roads not carved by tools, but by the quiet geometry of quantum reality itself. Photonic crystals and structural color. A color can exist without pigment, without dye, without paint, and without any chemical stain at all, born instead from the way light gets trapped, scattered, and filtered by tiny architecture. This is the strange beauty of photonic crystals and structural color, a subject that turns one of the most familiar experiences in your life, seeing color, into something much deeper than it first appears. When you look at a red apple, a blue shirt, or a painted wall, it is natural to think color comes from substances that absorb some wavelengths of light and reflect others. Pigments work this way. A pigment molecule has a certain chemistry, and that chemistry decides which parts of white light are swallowed and which are sent back to your eyes. But structural color is different. It does not begin with a colored chemical. It begins with shape. It begins with layers, ridges, holes, spheres, or repeating patterns so small that they are close to the size of visible light itself. When light meets those tiny structures, some wavelengths reinforce each other, some cancel each other, some bounce away, and some are prevented from moving through in certain directions. The color you see is not painted onto the object. It is selected by geometry. That is why some butterfly wings can appear electric blue even though they contain little or no blue pigment. That is why a peacock feather can shimmer green, turquoise, or gold depending on angle. That is why an opal seems to hold shifting fire inside a stone. The material is not glowing with inner magic. Its microscopic structure is arranging the journey of light. A photonic crystal is one of the clearest examples of this idea. A material with a repeating pattern of optical properties that can control which wavelengths of light pass through and which are reflected or blocked. The name photonic crystal can be slightly misleading if you imagine a normal crystal like quartz or salt, where atoms repeat in a lattice. In photonic crystals, the repeating structure is usually larger than atoms, often on the scale of light waves, and it affects photons somewhat like the repeating atomic structure of a semiconductor affects electrons. In simple language, it creates allowed and forbidden paths for light. Some colors can move through, others are reflected, others become trapped or guided. This is why photonic crystals are sometimes described as materials that shape light the way roads shape traffic. The light has not changed its nature. The environment has changed what the light is allowed to do. And this is where structural color becomes more than a pretty effect. It shows that color can be physical rather than chemical, architectural rather than molecular. If the spacing in the structure changes, the color can change. If the viewing angle changes, the color can shift. If humidity causes a soft photonic material to swell, the reflected color may move from one part of the spectrum to another. If pressure compresses the spacing, the color may respond. In other words, the color can become a sensor, a visible sign that something invisible has changed. This is why researchers study structural colors for anti-counterfeiting marks, responsive coatings, environmental sensors, cosmetics, textiles, displays, and materials that could keep their color without relying on traditional dyes. But the truth must stay careful. Structural color is not automatically better than pigment in every way. It can be brilliant, but it can also be angle dependent, meaning the color changes when you move your head or when light comes from a different direction. That shimmering effect, called iridescence, is beautiful in a butterfly wing or opal, but not always desirable for paint, fabric, packaging, or screens where people may want stable color from every angle. Some structural colors require extremely precise nanoscale fabrication, which can be expensive or difficult to scale. Some are fragile. Some lose their effect when the structure is damaged, filled with dirt, covered by oil, or worn down. Some artificial photonic materials are hard to make over large areas with consistent color. So the real promise is not that structural color will replace every pigment overnight. The real promise is that it gives us a second language of color. Pigment says, choose a molecule. Structure says, choose a pattern. Pigment asks what chemistry absorbs. Structure asks how light waves interfere. Pigment can fade because chemical bonds break under sunlight. Structural color can sometimes resist fading better because the color comes from geometry. But if the geometry is damaged, the color can vanish or shift. Both have strengths, both have weaknesses, and sometimes nature combines them, using pigments and structure together to create colors richer than either could create alone. This is why a bird feather or insect wing may be more complex than a simple rainbow surface. Pigment can absorb unwanted background light, while structure reflects a sharp color, making the final appearance more vivid. Nature has had millions of years to experiment with these optical tricks, not for human beauty, but for survival, attracting mates, warning predators, blending into surroundings, confusing the eye, or signaling identity. A butterfly's wing is not trying to look artistic. It is using light as information. And when humans study that wing under a microscope, we find not paint, but architecture. Scales, ridges, layered surfaces, tiny repeating forms, all tuned to interact with light. That is the humbling part. Some of the most beautiful colors in the living world are not applied to the surface. They are built into it. The color is not a coat. It is the structure speaking. Photonic crystals take that lesson and make it deliberate. Engineers can design repeating arrangements that guide, reflect, or filter light in controlled ways. In optical fibers, microstructured materials can influence how light travels. In photonic chips, researchers hope to control light on small scales for communication and sensing. In sensors, a photonic structure can change color when it absorbs a chemical, stretches, swells, dries, heats, or bends. In security printing, structural colors can create effects that are difficult to copy because the hidden nanoscale pattern matters as much as the visible image. And in art and design, structural color opens the possibility of colors that are not mixed like paint, but grown, printed, assembled, or etched into surfaces. Yet even here, the best science does not pretend the path is simple. Making a stunning color in a laboratory sample is not the same as making a durable product that survives sunlight, rain, scratching, washing, bending, manufacturing variation, and years of use. Structural color depends on order, and order is difficult to preserve in the messy world. But that difficulty is also what makes the field so fascinating. It sits at the meeting point of physics, biology, chemistry, materials science, and design. It asks us to think of color not only as an appearance, but as a process. A surface becomes blue because light waves return from it in a particular pattern. A wing becomes iridescent because tiny scales are arranged just so. An opal becomes fiery because silica spheres are packed at distances that diffract light. A synthetic photonic crystal becomes a filter because its repeating structure creates a forbidden range for certain wavelengths. Suddenly, color is no longer passive. It is an event happening between light, structure, and your eye. Without light, the color is silent. Without structure, the light has no selective path. Without an observer, the experience of color never becomes sensation. And that should make you question the ordinary world more deeply. The blue of a morpho butterfly is not simply on the wing the way ink is on paper. It is produced when light meets nanoscale ridges and returns to you transformed. The rainbow in an opal is not a secret liquid fire, but the consequence of order hidden inside a stone. The shimmer on a beetle shell may be a survival strategy written in optics. The world is full of colors that are not substances, but relationships. This is the quiet philosophical weight of structural color. It reminds you that appearance is not always a layer placed on top of reality. Sometimes appearance is reality structure made visible. What you see is the result of spacing, scale, angle, wavelength, and order. A tiny pattern too small for your eye to resolve can decide the color your eye receives. The unseen builds the scene. And maybe that is why photonic crystals feel so profound. They show that matter can control light, not only by absorbing it, but by organizing space for it. They reveal that emptiness between structures can matter as much as the structures themselves. They teach that a surface can be a kind of instrument, playing certain wavelengths and muting others. A pigment is like a voice with a natural tone. A photonic crystal is like a flute, where the shape of the chamber decides the note. Both can make beauty, but one does it through chemistry and the other through architecture. So the next time you see a butterfly wing flash blue, an opal shift with hidden fire, or a feather glow with impossible green, remember that you may not be looking at color in the usual sense. You may be looking at light being organized, selected, and returned by structure. You may be seeing geometry made visible. You may be watching matter whisper to light in a language too small for your eyes to read directly, but bright enough for your mind to feel. Plasma as a fourth state of matter. Plasma begins when matter becomes so energized that atoms can no longer keep all of their electrons close, and suddenly the material is not just hot gas, but a charged, restless sea that responds to invisible fields. This is why plasma is often called the fourth state of matter, after solid, liquid, and gas. But that simple classroom phrase barely captures what makes it strange. A solid has particles locked into place, a liquid flows while staying together, a gas expands and fills its container, plasma goes further. Some electrons are stripped away from atoms, leaving behind positively charged ions and free-moving electrons, so the material becomes electrically active in a way ordinary gas is not. NASA describes plasma as ionized matter, a state made of particles that have gained enough energy for electrons to separate from atoms, and this charged nature is what gives plasma its unusual behavior. In a normal gas, particles mostly collide, drift, and spread. In plasma, charged particles also feel electric and magnetic fields, and because they create fields of their own as they move, the whole system can organize, twist, ripple, arc, glow, and behave collectively. It is not just a crowd of particles, it is a crowd where every charged member is connected to forces reaching beyond direct contact. That is why plasma can form lightning, auroras, solar flares, glowing signs, fluorescent lamps, welding arcs, and the fire-bright matter inside stars. It can be hot enough to exist in the core of the sun, yet some laboratory and technological plasmas can have energetic electrons while the overall gas remains much cooler than a star. That detail matters because plasma is not defined only by temperature. It is defined by ionization and collective electromagnetic behavior. A candle flame may contain small amounts of ionized material, but it is not the same as the highly ionized plasma inside the sun. A neon sign glows because electricity excites gas atoms, and plasma-like behavior appears inside a tube, but it is not a miniature star. Lightning is a brief channel of plasma cut through air, a sudden conductive path where molecules are torn into charged pieces, and the sky becomes an electrical circuit for a fraction of a second. The aurora is plasma poetry written above Earth, where charged particles from the sun are guided by Earth's magnetic field and collide with atoms high in the atmosphere, creating curtains of green, red, and purple light. None of this requires myth. The truth is already luminous. Plasma is also often described as the most common visible state of matter in the universe, because stars, the solar wind, nebulae, and much of the space environment are made of ionized gases. Even though plasma feels rare here on Earth, because our everyday temperatures and pressures favor solids, liquids, and neutral gases. The ordinary world hides plasma from you because Earth's surface is a calm, cool place compared with stars and storms. But look upward, and plasma becomes almost the default language of the cosmos. The sun is not a ball of ordinary fire. Fire is chemical burning, while the sun is a vast sphere of hot plasma shaped by gravity, magnetic fields, and nuclear fusion in its core. Solar flares and coronal mass ejections are not simple explosions like sparks from a campfire. They are magnetic events where plasma and magnetic field lines rearrange violently, sending energy and particles outward into space. When that solar material reaches Earth, it can disturb satellites, power grids, radio communication, and navigation systems. So plasma is not only beautiful, it matters. It links the surface of the sun to technology on Earth. It turns space weather into something humans must understand. And this is one of the strangest parts. Plasma is difficult because it is collective. You cannot fully understand it by watching one particle alone. A single free electron is simple compared with billions of electrons and ions moving together, making waves, shielding charges, forming filaments, and responding to magnetic fields. Plasma can carry currents. It can create instabilities. It can form structures that look like ropes, sheets, loops, and jets. In fusion research, plasma becomes both the fuel and the challenge. To make fusion on Earth, Scientists try to heat light atomic nuclei until they can merge and release energy. But no ordinary container can hold plasma hot enough for fusion because the material would destroy the walls. Instead, devices such as tokamaks use powerful magnetic fields to confine the plasma, trying to keep the charged particles suspended away from direct contact with solid surfaces. This is not easy. Plasma wriggles, leaks energy, develops turbulence, and reacts to disturbances. It is like trying to hold a storm with invisible hands. But the pursuit matters because fusion could one day provide a powerful source of energy if scientists can make it sustained, controlled, and economically practical. That "if" is important. Fusion is real physics, but practical fusion power is still one of the hardest engineering goals on Earth. Plasma makes it possible and difficult at the same time. It is the substance of the dream and the obstacle inside the dream. And beyond fusion, plasma already serves many quieter roles. Plasma processing is used in making computer chips, where reactive plasmas help etch tiny patterns into materials. Plasma can clean surfaces, modify coatings, sterilize tools, treat materials, and create thin films. In medicine, cold plasma is studied for wound treatment and sterilization, though applications depend carefully on dose, safety, chemistry, and biological response. In industry, plasma torches can cut metal because ionized gas carries enormous energy into a focused region. In displays and lighting, plasma once played a major role in plasma TVs and still appears in lamps and signage. So the fourth state of matter is not only cosmic, it is technological. It is inside factories, laboratories, hospitals, satellites, and energy experiments. Yet it remains strangely underappreciated because it does not fit neatly into the substances you touch. You can hold ice, pour water, breathe air, but plasma often glows, burns, arcs, or floats beyond easy contact. It seems less like a material and more like an event. That feeling is understandable, but plasma is matter. It has particles, density, temperature, pressure, and motion. It can be measured, modeled, confined, heated, cooled, accelerated, and used. Its strangeness comes from charge. Once matter becomes ionized, it stops behaving like a neutral collection of atoms and begins participating in electromagnetic life. Electric fields pull the positive and negative particles in opposite directions. Magnetic fields bend their paths into spirals. Moving charges create currents, and currents create magnetic fields, which then shape the plasma again. This feedback is why plasma can feel almost alive when you watch auroras ripple or solar loops rise from the sun's surface. But it is not alive. It is matter responding through fields. It is nature showing that interaction does not always require touch. A magnetic field can shape plasma across distance. An electric field can accelerate particles without hands. A plasma wave can carry energy through a medium that looks almost empty. And if you think about that quietly, plasma changes how you see emptiness itself. Space is not simply blank darkness between planets. It is filled with thin plasma from the sun, with charged particles streaming outward as solar wind. Earth moves through that charged environment while its magnetic field carves out a protective bubble. Above you, long before space becomes truly distant, the ionosphere contains plasma that affects radio waves and communication. The sky is not just air fading into nothing. It is layered with charged matter, invisible currents, and electromagnetic boundaries. Plasma makes the space around Earth active. It makes the universe electrically textured, and perhaps that is the deeper lesson hidden inside the fourth state of matter. The familiar states you learned first are not the full vocabulary of reality. Matter can become solid and stable, liquid and flowing, gas and free. But it can also become charged and collective, glowing under fields, shaped by magnetism, carrying currents through space, forming stars, storms, and auroras. Plasma reminds you that the universe is not mostly quiet substance sitting still. Much of it is active, ionized, moving, connected across distance by forces you cannot see. A lightning bolt, a neon tube, a solar flare, and the glowing arms of a nebula may look like separate wonders, but they all belong to the same deeper family. Matter awakened into charge, and when you understand that, plasma stops being just the fourth state on a list. It becomes a doorway into a universe where matter is not only something you touch, but something that can glow, stream, spiral, and answer the invisible architecture of electric and magnetic fields. Programmable matter concepts. Programmable matter is the idea of making physical stuff behave less like a fixed object and more like a material with instructions hidden inside it. At first, the phrase sounds almost impossible, as if a table could suddenly become a chair, a wall could flow into a staircase, or a tool could reshape itself in your hand the moment you need something different. That version belongs more to science fiction than to today's engineering. But the real concept is still powerful. Programmable matter means building materials, particles, modules, or structures whose shape, behavior, stiffness, color, connection, motion, or function can change in a controlled way. It is not one single technology. It is a family of ideas stretching from modular robots that rearrange themselves, to 4D printed structures that change over time, to responsive materials that bend, fold, swell, stiffen, soften, assemble, or disassemble when triggered by heat, light, electricity, magnetism, moisture, chemicals, or mechanical force. MIT has described programmable matter research through examples such as reprogrammable materials that selectively self-assemble, while modular robotic systems and 4D printing are widely discussed as practical routes toward matter that can be reconfigured rather than permanently fixed. The key is to separate the dream from the reality. We do not yet have a bucket of dust that can instantly become a phone, a spoon, a drone, and a medical tool on command. We do not have millions of tiny robotic particles safely crawling into any object you imagine. We do not have a universal substance that obeys human thought. But we do have early forms of the same philosophy. Matter can be designed with a response. A strip can fold when heated. A printed lattice can curve when it absorbs water. A swarm of small robotic modules can connect into new shapes. A soft material can become rigid when locked into a new configuration. A surface can change texture or optical behavior. A structure can be printed flat and later transform into a three-dimensional form. These are not illusions. They are controlled changes built into the material's design. In traditional engineering, if you want a machine to do something different, you add more parts, motors, hinges, sensors, screws, wires, gears, springs, processors, pumps. Programmable matter asks a quieter question. What if some of that behavior could be moved into the material itself? What if the material were not just the body of the machine, but part of its intelligence? Not intelligence like a mind, but intelligence as response, as encoded behavior, as a rule waiting for the right trigger. A 4D printed object, for example, begins with 3D printing, but adds time as part of the design. The printed structure is made from materials that react to a stimulus, so the object can change shape after printing. A flat strip may curl into a tube. A flower-like structure may open when placed in water. A lattice may change stiffness or bend along a programmed path. Nature already does this beautifully. Pine cones open and close with humidity. Plants move as tissues swell and shrink. Seed pods twist and release stored stress. 4D printing tries to borrow that logic, not by making the material alive, but by arranging active and passive regions so that swelling, shrinking, heating, or softening produces a predictable transformation. Recent research describes 4D printing as a way to create shape-changing structures using stimuli-responsive materials, including reconfigurable metamaterials and devices that evolve after fabrication. This is one path toward programmable matter, not tiny robots crawling around, but geometry, material choice, and stimulus response working together like a physical program. Another path is modular robotics. Instead of one material changing internally, you build many small units that can attach, detach, communicate, and rearrange. Each unit might be simple, but together they can form larger shapes. This approach is closer to the science fiction image of matter made from tiny building blocks, but it is still extremely difficult. Every module needs power, control, communication, attachment mechanisms, movement ability, and reliability. As the modules get smaller, those problems become harder, not easier. A centimeter-sized robot can contain magnets, circuits, and mechanisms. A microscopic robot faces enormous challenges in power supply, manufacturing, control, heat, sensing, and coordination. Research on programmable matter through modular systems has demonstrated centimeter-scale modules and self-reconfiguration methods. But the gap between laboratory prototypes and free-flowing everyday programmable matter remains huge. That gap is important because it protects the science from becoming false hype. Programmable matter is not around the corner in the form of a liquid metal shapeshifter. It is an active research vision made of many partial successes, each solving one piece of the larger puzzle. One group works on self-assembly, where small parts find and connect to the right partners. Another works on soft robotics, where materials bend and stretch like living tissue. Another works on mechanical metamaterials, where architecture gives a structure unusual stiffness, motion, or deformation. Another works on hydrogels that swell with water or temperature. Another works on liquid crystal elastomers that contract or twist when heated or illuminated. Another works on magnetic particles, origami-inspired structures, robotic swarms, and programmable surfaces. None of these alone is the final dream. Together, they show a direction. Matter is becoming more active. The boundary between material and machine is becoming less sharp. A machine used to be something assembled from passive parts. A material used to be something chosen for fixed properties. Programmable matter blurs that distinction. It asks whether shape can be data, whether stiffness can be switched, whether a surface can remember multiple configurations, whether an object can be designed not only for what it is now, but for what it will become later. And that idea changes the emotional meaning of manufacturing. A normal object is born into a form and trapped there. A chair is a chair. A spoon is a spoon. A beam is a beam. If you want a different function, you need a different object. But programmable matter imagines objects with futures. Not unlimited futures, but designed possibilities. A medical implant that enters the body in one shape and unfolds into another. A spacecraft component that launches compactly and opens in space without heavy motors. A fabric that changes ventilation when the body warms. A soft robot that moves through a narrow space and then stiffens to support weight. A building material that adjusts shade, texture, or insulation. A tool handle that changes grip. A surface that guides droplets, sound, light, or heat differently depending on conditions. These examples are not all equally mature, and some remain experimental, but they show why the concept matters. The world is full of objects designed for one stable environment, even though real environments change constantly. Programmable matter is a way of designing for change. It says the object does not have to be perfect for one condition if it can adapt across several. But adaptation brings trade-offs. A responsive material may be slower than a motor. A self-folding structure may not be as strong as a solid part. A modular robot may be flexible but mechanically weaker than a single piece. A material that changes shape may fatigue, wear out, consume energy, or respond unpredictably outside the lab. A system with many small units may be powerful in theory but hard to coordinate in practice. A programmable surface may require complicated manufacturing. A smart material may work beautifully in a demonstration but fail after thousands of cycles in dirt, humidity, sunlight, vibration, or real human use. This is why the future of programmable matter will likely arrive first in narrow, practical forms rather than as universal shape-shifting substance. It may appear as adaptive medical devices, responsive textiles, deployable structures, soft robots, smart coatings, robotic collectives, reconfigurable antennas, morphing aerospace components, or materials that change mechanical properties on command. The revolution may not look like a movie scene. It may look like ordinary objects becoming slightly less fixed, one function at a time, and maybe that is more profound. The dream of programmable matter is not only about convenience, it challenges an old assumption that matter is passive unless a machine acts upon it. But the more we learn, the more we see that behavior can be embedded into structure. A printed pattern can decide how a sheet folds. A material gradient can decide where stress travels. A magnetic arrangement can decide how parts assemble. A molecular network can decide how stiffness changes. A swarm algorithm can decide how modules form a shape. In every case, the instruction is not floating outside the object. It is built into the object's relationships. This is the quiet philosophical core of programmable matter. Form is no longer just an outcome. Form can become a process. Matter can be designed not as a final answer, but as a question with several possible responses. And if that sounds strange, remember that nature has been doing something similar all along. A seed is not shaped like the tree it can become, but it contains instructions and materials that unfold under the right conditions. A protein folds into function because its structure and environment guide it. Bone remodels under stress. Skin repairs after injury. Leaves orient toward light. Life is full of matter that responds, adapts, and changes through built-in rules. Liquid crystals and digital displays. A liquid crystal is one of those rare materials that seems to stand between two worlds, flowing like a liquid while quietly keeping enough order to control light. That strange middle nature is the reason a flat screen can turn invisible electrical instructions into images, letters, faces, maps, movies, messages, and entire digital worlds. When you look at a phone, calculator, laptop, monitor, watch, or older television that uses liquid crystal display technology, you are not usually looking at tiny lamps that directly create every color in the simplest sense. In many LCDs, the liquid crystals do not produce light by themselves. Instead, they act more like millions of microscopic shutters, controlling light that comes from a backlight behind the screen or from reflected ambient light in simpler displays. This is the first quiet surprise. The image is not born from liquid crystals glowing, but from liquid crystals deciding how much light is allowed to pass. To understand that, you have to begin with the material itself. A normal liquid has molecules pointing in many directions, moving freely, without long-range order. A solid crystal has molecules or atoms arranged in a fixed, repeated pattern. A liquid crystal lives in between. Its molecules can flow past one another like a liquid, yet they tend to align in a shared direction, like a crowd all facing roughly the same way. This partial order gives liquid crystals their optical power. Light is not only brightness, it also has direction in the way its electric field vibrates, and that direction is called polarization. Most people never notice polarization in everyday life because the eye does not directly feel it, but LCDs depend on it constantly. A typical liquid crystal display uses polarizing filters, transparent electrodes, liquid crystal molecules, color filters, and a backlight working together in a thin layered system. The polarizers are like gatekeepers for light. One filter allows only light vibrating in a certain direction to pass. Another filter, placed differently, can block that light unless something twists the light's polarization between them. The liquid crystal layer is that something. In a classic twisted pneumatic LCD, the molecules are arranged so that when no voltage is applied, they guide the polarization of light as it passes through, allowing it to make it through the second polarizer. When a voltage is applied, the molecules rotate or align differently under the electric field, and their ability to twist the light changes. The pixel becomes darker or lighter depending on how much light gets through. In simple terms, electricity does not paint the image directly. Electricity changes molecular orientation. Molecular orientation changes polarization. Polarization controls transmission. Transmission becomes brightness. Brightness becomes the image your brain reads as reality on a screen. That chain is astonishing when you slow it down. A message appears because tiny molecules tilt. A number appears because a region blocks light. A face appears because millions of shutters open by different amounts. Each pixel on a color LCD is usually divided into smaller red, green, and blue subpixels, each with its own color filter. By controlling how much light passes through each subpixel, the display can mix colors in your perception. A red area on the screen is not necessarily a little red liquid shining by itself. It is often white backlight passing through a red filter, while neighboring green and blue channels are reduced. A blue sky in a video is millions of microscopic decisions about how much red, green, and blue light should escape at each point. And behind those decisions is a grid of electronics. In modern active matrix LCDs, tiny thin film transistors help control individual pixels, holding voltages steady so images can refresh smoothly and maintain detail. Without that kind of control, large high-resolution screens would blur, lag, or lose contrast more easily. This is where liquid crystals meet digital civilization. A molecule that can rotate under an electric field becomes part of a system that stores, gates, and modulates light across millions of positions. The screen seems flat and effortless, but inside it is a layered negotiation between physics and engineering. The backlight supplies illumination. Polarizers shape the light. Electrodes create fields. Liquid crystals reorient. Color filters select wavelengths. Transistors control timing. Software decides the pattern. Your eye blends the result. Your brain turns it into meaning. A single word on a display is not simply displayed. It is assembled from controlled light. And this makes LCD technology feel almost philosophical in a quiet way. The screen does not create the world you see on it as matter. It creates conditions under which light can be selectively withheld. Images are made as much by blocking as by revealing. Darkness is not absence alone. It is a controlled refusal of light. Brightness is permission. A picture appears because some light is guided through and some is stopped. That may sound poetic, but it is exactly what makes the technology work. Still, the science must remain honest. LCDs are not perfect displays. Because the liquid crystals control light rather than emitting it directly, they often need a backlight which can affect contrast, black levels, thickness, power use, and viewing quality. A black pixel in many LCDs is not always perfect darkness, because some backlight may leak through the layers. Viewing angle can change the perceived brightness and color because the optical behavior depends on direction. Response time matters because molecules need a finite time to reorient. If they move too slowly, fast motion can blur. Temperature can affect performance, since liquid crystal viscosity and molecular motion change with heat and cold. Manufacturing must be extremely precise because defects, dust, uneven spacing, and dead pixels can become visible in a finished display. And while newer display technologies such as OLED and micro-LED have changed the landscape by emitting light from individual pixels, LCDs remain important because they can be efficient, mature, scalable, affordable, bright, and reliable in many uses. The story is not that liquid crystals are the best solution for everything forever. The story is that they transformed visual technology by making it possible to control light in thin, flat, electronically addressable panels. Before flat displays became common, screens were bulky glass tubes, heavy and deep, shaped by electron beams and phosphors. LCDs helped move display technology into watches, calculators, laptops, portable game systems, phones, control panels, medical devices, aircraft instruments, car dashboards, televisions, and countless everyday tools. They made information thinner. They made screens portable. They changed how humans carry images through daily life. And all of that depends on matter that is neither fully liquid in the ordinary sense, nor fully crystalline in the solid sense. It is organized enough to steer light, fluid enough to respond. This middle state is the heart of the wonder. Most of us are taught categories as if they are walls. Solid here, liquid there, gas somewhere else. Liquid crystals show that nature often prefers thresholds, blends, and partial orders. A substance can flow while keeping direction. A material can be soft and still optically disciplined. A molecule can be free enough to move, but ordered enough to matter. That is why liquid crystal science became important far beyond screens. Liquid crystals appear in thermometers, sensors, optical devices, scientific research, biological membranes, and soft matter physics. Pierre-Gilles Degenerate received the 1991 Nobel Prize in Physics for showing how methods used to study order in simple systems could be extended to complex forms of matter, especially liquid crystals and polymers, reminding us that liquid crystals are not just industrial ingredients, but a gateway into understanding order and disorder itself. When you look at an LCD then, you are not only looking at a device, you are looking at a practical use of a deep physical idea, that partial order can be controlled. The screen is a disciplined fluid field, a sheet of molecules obeying electrical signals fast enough that your mind forgets the machinery. You swipe, type, watch, scroll, pause, read, and the whole layered system keeps translating voltage into light. It is easy to take this for granted because screens are everywhere now. Their magic has become ordinary through repetition. But if you pause, the strangeness returns. A layer thinner than a thought can decide whether light reaches your eye. A molecule's orientation can become a pixel's brightness. Millions of tiny regions can coordinate quickly enough to create motion. A liquid-like material can become the boundary between private electrical code and shared visual experience. That is the quiet power of liquid crystals in digital displays. They do not shout. They do not glow like fire. They do not look dramatic when hidden inside glass. But they turned light into something programmable, not by generating it, but by guiding and filtering it with molecular order. And perhaps that is the final lesson of the screen in front of you. The digital world is not only software, not only data, not only invisible signals moving through circuits. It also depends on matter with unusual states, on molecules that can align, rotate, and reshape the path of light. Every image you see is a collaboration between code and crystal, between electricity and alignment, between human meaning and a material that lives gently between liquid freedom and crystalline order.